Okay, back to action here to try to finish this task. So where we were is we have to deal with like lambda callbacks. We have to deal with some last offset adjustments and these types of things. In fact, I don't exactly remember what we need to correct next, but we can figure this out pretty quickly. I mean, I can see index start topo offs are adjusted. So is unsat and sat offset. Now, we don't actually necessarily want to use absolute addresses. One second. Yeah, so we don't want to necessarily always use these absolute addresses like we're doing with 8 bytes when we could use 4 bytes. But when we're going to interoperate between code that's in C and code that's in the assembly area, or even if we're referring to data or whatever the case may be, the relative 32-bit address may have a virtual memory address that's more than 32 bits of displacement off. As far as I know, we don't need to worry about the segment register aspect of things. So, and in fact, we can already see, because we can already jump into the code. We've already shown that we can start executing it. Of course, it's crashing, but what we do need to do are those addresses. But some of these that are actually relative offsets, we shouldn't need to adjust like this at all. And we should think about that. Like the counter offset that we need to do right now. Counter offset. So if we look at this, we go find the counter offset. And it's 52, so it's this, yeah, this location. Oh yeah, we need to redo all the offsets, that's right. Okay, yeah, that we better do that first. Again, this is something that should be automatically generated eventually. We shouldn't necessarily be doing it like this. So the index offset is at E. Oh, that's already right. The counter offset is at 56 now. So it jumped a few bytes because we made a correction in the assembly. Okay, so 56. Top op stack is at 71. Oh. Yeah, we don't need to fix this one, do we? Yeah. Since this is comparing the stack pointer, invariably we will need the full 8 bytes. I mean, you really have to think about it. Every case here you have to think about. The next one's the get successor node address. That's at 8E. I'm guessing everything's 4 bytes, yeah. So, wait a second. It's not 4 bytes. That's actually 8 bytes. Oh, yeah. And start topo offset is now a DC. Whoa, the code is totally different, huh? That's 7 bytes? Check same SCC offset. I don't see it. Check same SCC offset. Unsat is this offset, 15A. add solution offset is 171. The sat offset here is 181. It's just weird, these are like only 4 bytes off again, so I forgot the change we made though, so it's okay. Okay, but this should be the check same SCC offset. Oh, no, no, no. It's not this. This actually is being set already. It's this one. I see we're saying +1, +1, +1. Doesn't look right. Okay, this is gonna take a while, so I'm pretty much expecting to be stepping through an assembly language and figuring all of this stuff out. So let's look at the counter offset look. Okay, counter offset we already said means. Did we set that one already? I think we solved it already over here. Oh, this is tricky. No, I see check the same SCC offset. That we do check, or we do try to adjust. Okay, so there's no. What about get successor node offset? We already have done that one. Again, I'm not sure if any of these are working. Counter offset we definitely haven't done yet. Add solution offset, we've done it. Oh wow. Sat offset we've done, unsat. So the only one I see left to do is the counter offset, and that also is going to be per node. So we just kind of drop right over into here. We just kind of capture the. Oh wait, we are capturing it. Oh wait, we do set it. Oh okay, we're done. Actually, we are done. Okay. Shoot for the moon. Hope that it works. Probably not, but I mean, never hurts to try. I mean, this isn't bad because this is only 8 locations we have to hand copy and paste. And honestly, we can make something to automate this from the list file. But I'd like to get a little more wisdom on just the scope of what we're trying to do here, because you don't know if there's going to be more details that we're going to have in the future. Probably not much, but maybe some. All right, so the only thing to do is to look at the disassembly now. And if it's, again, what we can do here is just look at it, and if we don't know what's going on with it, then we're going to have to regroup. So what I see is we're moving the RCX to FFFF, which, and then we're, of course, whoa, that looks messed up. Subtract ESP8, move the RCX. Okay, so this is like really not getting anywhere right now. This is really, really still at the beginning, I think. It's fine. That actually to be expected. But it's this next line of code that concerns me as we see the move to the RAX. Um, what's at the RCX? Ah. Okay, so this is wrong. This is definitely wrong. Um, and it's weird because we see E, and address E should be the instruction here. So we've got 4 plus 2 is 6. Uh, wait a second. Something's wrong. Immediately, we see something's wrong. We're missing 2 instructions. Oh. Oh, that's... Yeah, that's weird. Okay. Let's just run our little parse program again and see what comes out and see if we just miscopy pasted something. Oh, wait. No. I see the 48B8. Yeah, it is at E. Plus 2. Yeah, I mean, this looks right. This looks right. So we can comment that back out. Now we want to kind of look back at our blueprint and just see what is going on here. Yeah, this is kind of a slow process here, but again, it's the first time it is the slowest. If we want to kind of, no, it is missing code. Okay, I see. It is okay. Oops, spoke too soon there. That was exactly what I needed to do. So it's missing like the first line or two. I guess I miscopied and pasted this. So if I look here, I see 4883 ECO8, 4883 ECO8, and somehow where did these 2 lines go? And of course, then all the stuff we're doing it would end up being wrong, and it's just yeah, as simple as that. So, oh no, don't run that again. We don't need this program. Comment that out. It's useful for having that there, but kind of just using that temporarily. I would build it into some sort of more formal process. Like the build process could call another binary that just generates assembly listings, generates blueprints for us. That actually we should do that, but it's like not like an urgent task. Okay, so probably, oh, okay, so RCX actually, okay, I'm looking at the values. Probably these aren't visible because I'm, oh, C, 0. Okay, that's definitely an interesting problem. So racks, now one of the things we should open in here is the memory view so I can, just see what's going on. Probably we know the problem already. The problem is index I've defined as an integer, but it needs to be a 64-bit integer. I mean, these are obvious things. Obviously, we could change it to 32 bits. There's no reason we couldn't do that. Again, we just need to make up our mind one way or another. It would be faster probably with 32 bits, without a doubt. 64-bit stuff is faster for like arithmetic, but not if we're doing this kind of self-modifying code, immediate data stuff. Of course, it would be slower. So, this is an engineering question. We could engineer it either way. Where There's the memory window. Okay, actually, I don't even need to open the memory window here. I already know what the problem is. So, well, actually, I don't. I know one problem. I don't know the reason it crashed, though. I know that obviously this next line is the real problem because it's moving to the FFFFFDF, the racks. Actually, you know, the hope right now is that that would work. So, what was the error? Access violation. Oh, so it tried to write an absolute memory address? But we don't want it to write an absolute memory address. We wanted this to be an... Okay, so it's... Oh. This is going to be annoying, because this is purely addressing mode stuff right now. The assumption was that this was going to be like a relative code address. But here, this is why this is a very tricky assumption, because the RIP, the instruction pointer relative addressing model, really usually has to do with like jumps and calls and stuff. And for these data instructions as well somehow, but we're going to have to go dig out the details. There's no way around that. Of course, I saw another bug, but that really isn't the main issue here. So this should be like a unsigned, or can be a signed one. We don't really care. The same would go for start topo, but it's already a pointer, so we've already taken care of that. It'll automatically... Now, again, if we're going to do a 32-bit build, we won't want this to be 64 bits, so we would want to use like a type that's compatible there. And again, we need to make sure it would work on Windows and Linux. So, okay, whatever. Fix up the type there. But again, I haven't fixed anything here. I've just like, made it so we have to figure out how to do RIP relative addressing in the x64 world. So what I'm looking at is a web page talking about from the Intel instruction manual, and it says that the modRM byte is going to select RIP relative addressing. This starts to become where probably we're just going to start rewriting to grab the addresses that we want out, because another option we could do is we could just look for certain code snippets. We could just do like something like a memory find operation for like little snippets. That's not my favorite way right now. My favorite way is to put some kind of metadata that would like tell how to generate these constants. And again, probably that would just be a comment in the assembly file, which makes it into the listing file, and we could parse a special thing, maybe put a special tag around it that says, hey, this variable plus some offset, +1 +1 or something, because obviously it needs to deal with this. But then actually what you would want to do is you would want to say, when you're saying like +1 +1, you wouldn't necessarily want to say that, but you would want to say like find the 4-byte or the 8-byte argument. So you would actually want to do it even more elegantly, because you know that you're going to have a placeholder that's like a block of bytes. Now, do those always have to be on separate lines? No, they don't. Really, the problem here is this is like, the way this is formatted, you can even have 2 lines here, you can see. So, yeah, parsing this is not a nightmare, but it's annoying, needless to say. But we've already gotten a decent crack at starting to be able to parse such a listing. So we don't have to write our own assembler, basically, get into those details, but apparently we do because we're not getting the rip relative here. Now the question is, could we do this? Again, maybe I started confounding the jump instruction here, and it's almost certainly what I did. I think I confounded this jump instruction. Uh, I don't know, because actually that's a simple EB jump instruction. I don't know where I went wrong with this, but obviously the idea of using rip relative addressing somehow came up short. The problem is this is a label here, and yeah, if you turn this into a displacement, you know, I've done this before, and I may just want to go dig out the project where okay. Okay, rip is an undefined symbol. You know, I'm sure what we want to do is possible here. The question is, can I trick the compiler into emitting the right opcode? So one question is something like putting even we could define a data byte just to see what's going on here. Yeah, do you see what happened here? Which must be in the relative addressing mode. Okay. So what we can do is some kind of a hack here. We all like hacks. So what we want to do is we want to tell it to not, oh man. So it's going to change all the offsets again. This is just going to be, well, let's make sure we can get the addressing mode working correctly. The only thing I can see is that we want to like add node adder loc yet again because it's 0 to make it, oh, cannot add two relocatable labels. What if we do this first? Then it works. What do we get in here? Yeah, look at that. Look at that. That's a beauty right there. That's a beauty. Because what we're doing is we're saying everything's relative to node adder loc anyways. So we're really playing games here. We're doing like a pointer subtraction, but then we're adding it back to a pointer. So actually we do need this node adder loc here because it would be confused if you just did this. It would be a pointer plus a pointer and it would get... So again, we're doing some really low level kind of deep understanding of how the assembler works so that it will compute correct offsets for us. At the same time that it does that, it gives us rip relative addressing, which is, as I said, going to be extremely important and quite elegant, quite frankly. It's going to be really nice if it works. In fact, I see no reason why it wouldn't work. I think we're good to go. The only problem is the -8 here looks questionable because it probably should be -7 now. This is absolute maddening. Oh, let's see somebody message me in the chat. All right. Oh, I think they already left. What am I doing? Well, I've answered it now, but a little late. Okay, so that is what I'm doing, and here I can see that I changed an 8-byte instruction to 7 bytes. So you see everywhere I put 8, because I thought it changed to 8 bytes, but I didn't realize it was changing the addressing mode. So we go to back to 7 bytes, and yeah, this is gonna be like a total nightmare to like try to figure all of this stuff out so precisely. How can I get all of this done? To me, right now, what I'm worried about is having to uh, keep recompiling this code. If the sizes don't change, I don't care. But if the labels are going to change, this is going to be a nightmare scenario here. So the key is to like look for dollars here, because anywhere we use dollars, we wanted to use RIP relative addressing. Not there. Not there. 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 Fix it. Fix it. Okay. Okay. Some of these load effective address and pushes may not have the problem because we're not doing the dereferencing there. This is just, yeah, this is so, it's so diabolical. Mainly what I'm worried about is having to keep playing games with recompiling here. I, of course, don't want to do that. I don't want to like keep recalculating these offsets. At least I hope that the blueprint will stabilize now. Because the amount of time it's going to take to do this task directly correlates to how long it takes to get this blueprint right. The faster this is all correct, the faster to move on to something else. So the hope is this code's starting to become right. So we move on to this. We're assuming a lot of these addresses will be the same. E is the same. Counter offset. It's now 50. Oh man, they're all going back to the old values. Surprise, surprise. Because we changed 6 instructions right before. So hey, now we can think about why this is all happening. Get successor node adder. I think it's. I think 86. Oh, yeah, that's why this is 8 bytes here. So there's good explanations for all this. Start topo is a D1. Check same SCC. We do that here. Aha. We do that at 145, and it's gone back to. Okay, we're just yo-yoing all over the place. What? Oh man! So I didn't actually need to change anything. I just needed to trick the assembler to give what actually is desired here. So 14E is unsat. And add solution is 165. And sat offs. Sat offs is this one. Whew. Okay. Let's see what happens. Shoot for the moon. Oh wait, did I? Yeah. Just tell me it got like a little further. Oh. Wow. Wow. Really? Wow, look at this. Move rack 0, return. It's working. You know, this is where you get a smile on your face and you say, oh, wow, it is actually working here. Now the problem is it called RDX. Now we're getting to the lambda in C. Oh, this is so beautiful though, because we're already calling into C code and now we can deal with that Whoa. Whoa now. Okay, what was RDX? 0? No, it was this address. So what's at this address? Now we go into memory and we probably want to like figure out just what's going on. We know this is a standard function and we're not going to just be able to call it that easily. So what we see here is that there's no code probably. What I see is a 64-bit pointers. I see four 64-bit pointers. So what I imagine is that this address that we're calling is actually the this pointer. So we've got the this pointer for a standard function, and we need to know where operator parentheses is. And it's a good question. So is there like a dereference we can do here? I forgot how you... Dereferencing a memory address in the Visual Studio debugger. Okay, so it says just use casting. So here's what I'm going to do. I'm going to go over to the watch window and we're going to like kind of be clever here. We're going to say that's a pointer, but let's change this again. And let's say, hey, standard function. I don't know if it'll accept this or not. Void star. Ooh. It's really too bad. Oh, that's really too bad. Because this would have been quite nice. Well, since that didn't work, we could just use like long pointer and dereference. But again, it's kind of like, what are we looking at here? The truth is we don't exactly know. The first pointer would be like maybe a base class. Again, this is some kind of a template class. So we could, you know, we could also say plus, okay, plus 8, I guess. Oh yeah, I mean, it's just pointer soup around here. And if we don't know, yeah, it won't do that one. Okay, this one has 2 pointers. Some of these could be like, the first one actually, well, some of these are data members, who knows, right? So again, this is just playing around. So there's no This is also another pointer. The only thing we want to know is how to get to operator parentheses. The ideal thing would be to know the way to get to it without, you know, having to worry about, is it a debug, is it a release, is it this STL library or that STL library. The truth is we want to know the address in the V table. So another thing I'm going to just look really quick is how do you get the address of a function in V table C++? Currently, there's no way of doing this. Okay. GCC has an extension where you can put a star in front of the name. Oh, yeah, I don't know if any of these are going to work. So one cool thing that we can do here is we can just run again, and we can just go to the disassembly right now because we're calling a lambda, and we can kind of see what's happening. So here we see this, you know what I mean? Here's the this pointer. It's giving us a little bit of a clue of what's happening here. Yeah, you can see this is okay. What you can see here is we do not want this much code in our self-modifying code. We do not want this muck mess in there. This, I mean, you can see how ridiculous this is. It's now this, remember, is the this pointer for this lambda, not the lambda we're calling, but the lambda we're in here. So we don't need to care about that one as much. And so it gets racks plus 10 into racks, which is probably one of the captures. So first it moves racks this. What is this? I don't know exactly. I would assume it's the CX register. Yeah, that's kind of vague. Probably it's weird. Yeah, it's weird that it doesn't, it just puts a label that's not defined anywhere. But it doesn't really matter. Oh, look, check for debugger just my code. It's got some like little tricks it's doing for the debugger. Anyways, it moves RCX to this again, and so it's going back. It moves the CX to CX. It moves the CX. What's at the CX? It multiplies by 181. And so what we're seeing is we're seeing this computation right here. So 181. This computation is doing this multiplication size of blueprint times I. We don't care about any of that. That's not helping call the lambda. We're watching it get I. So these RCX operations are getting the capture variable I, and then it multiplies by 181. So you can see it's a pointer to a pointer to a pointer. So the first pointer in the lambda is actually the captures. So the lambda contains a pointer with another pointer which points to points to a structure, and that structure contains all the captures, whether they're by value, by reference, and then this one, the racks has taken this and racks plus 10, and we don't know what it's doing with that yet though, so let's just hold on. And then it moves racks, what's at the racks. Again, it's getting this P code block, I think, here, right? Yeah, because then it loads it. Okay, so far, it's done nothing. Actually, all this code is only the computation here. It has nothing to do with calling the lambda yet. Then we see it moving racks to this. Okay, so it gets the I variable again and it increments it. You see this inc EAX? That's I++. So far, all of this code has only been this part to get the lambda. It hasn't actually done anything with it. So where is the lambda right now? Well, actually, this isn't a lambda invocation. Oh, this isn't going to help us. Never mind. Oh, man. I just realized that. We're casting it to just a void function, so it's just going to call it. Just going to call it. Now it does, yeah, but saving something in the RCX, it doesn't really matter here. No, no. We're lost here. We're absolutely lost. Okay, what? After all that nonsense, let's figure this out very simply. This is not that hard. No need to make it harder than it is here. What we do is we make a lambda somewhere right here. So okay, so let's just make a lambda and call a lambda. I have an idea. Uh, Actually, this isn't a void one. This one takes an int and returns a void star. So let's just let's be very accurate in our test lambda. Okay. What am I doing wrong here? Oh, I forgot a semicolon maybe. All right. Now let's see what happens. Oh, is it going to say it doesn't do anything? Oh, I don't pass the number here. Okay, we'll pass 0. Just be very boring about this. It doesn't matter. Or generic, I should say. Must be some silly thing with that. Yeah. Uh, yeah, it's true. Returning null, it will somehow interpret that. I thought it would be a void pointer, but okay, whatever. We got it working. So now we go to the disassembly and we can figure out like a little bit of intuition on this. So we see it's going to use the EDX. Remember I said the RCX will be this pointer. So it's very simple. It moves test lambda into the RCX and then it calls it calls operator parentheses. I mean, it's so simple that this is too easy for us. We're to even call this a challenge is ridiculous. This is not challenging at all. This is easy. So all we do is load the lambda, the standard function. We don't call it. We load it into the RCX, and then we need to call this operator parentheses function. So the only thing, and we can put our conclusion, RCX equals test lambda call operator parentheses. So this is exactly what I said 20 times now that we're going to do exactly this. We know how lambdas work. As I said, this nothing really rocket science. We know the first pointer in the lambda data structure is the captures, which is also pretty cool to know. Okay, the capture is the first variable in the lambda structure. Although we don't care. For us, it's a black box. The thing we needed to know was the calling convention. We know it now. If we want to call the lambda from our self-modifying code, we need to load the ECX. So that means our model's wrong here. A model needs to not just call racks. It can't do that. So the problem is I see RCX being loaded here. And I'm not sure why right now. Okay, I see that we are checking things are on the stack. I see that we're doing some operations here. Question is, what are we doing right here? This is crucial. Oh, this one we're changing some code up here to peak. Oh, this needs to be fixed. Uh-huh. Yeah, this is changing it for the current node, not for the node that's being called. Oh, that is really... That's really tricky because we were doing that with a callback function before. Oh, that's tricky because we don't have a way of referencing other nodes except by the address that's returned from this callback. But actually, that would be sufficient. We'll have to fix that. Oh, yeah, these are going to be, oh man, I have a feeling we're going to be generating code and fixing offsets too much. We're going to have to fix that altogether. I'm going to have to like write a new offset this type of thing, and I don't even know, but we're going to do exactly that. We're going to write like a little meta tag in the model assembly so that we get all the offsets and we can just copy and paste them and be done with it. Okay, so call racks. Okay, so move RCX racks. Why would we do that? Racks is the counter. Oh, yeah. So the assumption here was that when we call the function, RCX is the parameter. Yeah, okay. All these assumptions are just wrong. We know that's not going to work. We don't need racks anymore, so yeah, why do we call... Oh, we call racks because this is the address. But now we know that when we call it, we're actually getting... The address we're going to call is turning out to be like a library function. It's going to be a fixed address. It's going to be like calling an extern here, so we don't need that. This is a fixed address. And what we can just do here is move the RCX, the racks. So whatever that returns, it's the lambda, and we just need to put that in RCX, and then we need to actually call operator parentheses. How exactly are we going to do that? Okay, we will use the racks. The same old, same old, same old. Now, another question is, do we need the operator parentheses pointer? We know that they all share the same code, effectively. There's no reason, but they won't share the same code except for the right specialization of the template. So actually, this should be like literally void star int. Again, the specialization is going to turn out to be important. Now, I don't know how we're going to get that pointer, but we can just initialize it now. And again, this won't work because we want to actually set this in the function that we're calling. We don't want to set it here. So this is wrong. We might as well fix it right now because, again, it doesn't make sense to delay the inevitable here. It just absolutely doesn't make sense. Hmm. So I'm going to say that this stuff here should all be done first. So we want to get the, oh, but this gets a lambda. It's not getting the node address. It's getting the lambda, which calls the node. Un Wait a second. I'm like twisting things around here. I need to check this again. That's wrong too. This gets, look at the lambda. It actually, no, it actually gets us code. It gives us an actual address. So all we need to do, oh, so that actually simplifies things. So all we need to do is, oh, that's actually, it's very good news here. So it means we do this up front. So before we even decide, oh, okay, but we don't need racks anymore. So, and we don't need to use RCX either. So we decrement, move. We decrement the counter and store it, and then we're at this top up stack loc, which is important because it needs to have that top up stack loaded. So we can, but what we could do is just do this right up front here. So we know that we're going to do something here, and so we can already just like load the RDX. Wait, okay, I'm totally like confounding myself here. There are some things here. Is just a call. Call loc should be just a call. I know we're starting to actually really fix this. This is nice. So this actually will be the call, but we're probably we're calling this lambda pointer. So it needs to initialize the RCX to this get successor node adder. Actually, it should be an RCX function, and it needs to take an RDX. So RDX will be racks. That's right. We know for sure we want that counter. Okay, so RDX is racks. Then we need to move RCX some 8-byte pointer. And this is actually the lambda. So, and then this needs to be the operator parentheses. And so since we are going to need an 8-byte pointer, we're going to have to use another register. But we have some good news here. And that's that we don't need racks anymore because we've stored it in the RDX. And actually we know the caller won't change it, but it doesn't matter because we don't need it anymore. We could always get it again from counter loc, but we don't want to do that either. So what we'll do is we'll just move racks. And again, this has to be fixed. It has to be the operator. Actually, we should put the comment here. So I think this will really work. I think we will actually now generate a code. It will load the RCX with the lambda pointer. It will then load RAX with this operator parentheses. If we can figure out a nice way to get that from C so that it's portable and compatible and everything, we call racks. Now we're going to get back the node address in our assembly self-modifying code block. So we're going to actually want to take that pointer, and we want that, say, to be in racks. It is in racks. So why do we care? Because we're going to call it. We're going to call it right here. We don't touch racks here, do we? No. We're just, oh yeah, this actually doesn't need to be, this is fine. Everything's fine, just get rid of this. Wow, that's it. And we're done. I mean, effectively, I think this is perfect. This has solved a whole bunch of problems now that we will never hit again, which means that we're down to the final like little details here. Because now we can call lambda functions from assembly language. We can actually interoperate between C and assembly. In fact, if we need it, and we're going to call from C, we're calling assembly using just kind of pointers to functions. And from assembly, we're able to call not just C code, we can do that, we don't even do it, but we're calling lambdas. We're doing something even more advanced. And we're doing it in 64-bit code where the calling conventions can be rather annoying. But this is going to work. I basically have zero doubts that this will work. Of course, it's a grinding process to get here. I mean, you can see how, I'm struggling to deal with all these little issues, but it doesn't matter because as I said, I'm going to solve them. It's like on a mission here, and we're going to do it. Uh, if you have the right amount of knowledge and experience, you can definitely solve it if you're willing to put the time and effort. And energy. It's about energy too, because this stuff is, for a lot of people, just wouldn't find it fun or would be too frustrated. But it's kind of fun if you make it fun, and that's what I do. I try to make this type of stuff fun because, well, uh, you know, I realize the power of this. After I do this one time, the next time I do it, I'll do it 2 or 3 times faster. And the time after that, it'll be 2 or 3 times faster. I'll put 32-bit code. I'll make this, portable to 32 bits. I'll make it work on Linux. All of a sudden, boom, 32-bit Linux. I'll have a ton of different flavors and options and be proving that, hey, I can do this anywhere, in any environment. I have a strategy for getting this type of code working. And I have some really general techniques for generating assembly. And even in Linux, we can take these lists and we can parse them. Probably takes some effort. But again, writing 70 lines of code to do some parsing is no big deal if it's going to get you somewhere. Okay, so we've done half of the job here. We're going to do the other half now, which is the other lambda we call. We call one more lambda, or do we call two? Yeah, we've got a lot of we've got a lot of problems here. We've got unsat, sat, sat, add solution, and all of these are problems. Okay, add solution's gonna take, does it take a param? No, it doesn't need to. We've actually used captures and stuff and making, although actually it might be more efficient to not generate so many lambda functions. Honestly, this is got to be the silliest thing ever. Well, it doesn't matter. Then we just push the argument in here. We move it to the CX. But here we don't need the CX. What we need is to load the racks and call the racks. And this will be the lambda pointer. And then we need the lambda pointer. So again, I think the neat thing to do here is to just say what's going on here. So say, hey, this is what is it, a void void, right? So, okay, so this is our void void operator. And this is this. This is the counterpart. Add solution, but it's a standard function pointer. It's an object in C++. But we just load it in the CX register. That's all you do, and you don't worry about it. Then we call, and okay, so fine, that's done. Again, we want to finish the blueprint. We don't want to stop changing this code. So I want to be very careful now to lay this code correctly so that I only have to change it as few times as possible. It'll just save time. Yeah, we can keep changing it and going back and doing all this, but I want to get the job done. And then I want to make it so we can automatically pull addresses out from our listing file. And we can regenerate, and we don't have to do any manual labor. We can literally get all the offsets of our self-modifying template spots where we use these -1s to force the assembler to give us 8 bytes, not 4 bytes. We're doing all sorts of nasty tricks because the ML assembler is not always flexible. Really, you want a really great assembler to do self-modifying code. You want one more powerful than ML. ML is not powerful enough for this. Instead, we're resorting to these types of hacks all over the place. And there may be better ways of doing it that I just don't know about. But I don't want to waste time on that because you can waste hours trying to find better ways of doing stuff. But if I have a workaround, it's good enough. For me, I'm only interested in using the assembler is a guiding tool. I could always write raw binary code. It's boring to do that. I much prefer to, write natural stuff and let an assembler do that work for me. And so I've kind of using this hybrid approach, and I think it's the best approach. I really don't think you can beat this hybrid approach because it's very fast and effective. And yeah, sometimes I fight with the assembler, but we win the fights. And we give up because this is good enough and it works perfectly and it's well understood. Again, 7, I should really put like 1 plus 1 plus 1 plus 4 to say that, okay, it's a prefix byte, an opcode byte, the RM byte, and then the 4 byte displacement. But again, we can fix that later. For now, I want to get this job done without having to relay out code again. So, okay, move RCX, jump RCX. We know it's wrong. Move RCX, actually that's very good, right? So what's unsat? I think it's just a function void. But when we jump, now jumping to operator parentheses seems like you're just asking for trouble, but you're not. As long as the stack has a good return value, you're not. You're in perfectly good shape. And our stack should have a perfectly good return value. So actually, we just want to jump to like the racks. And we're just going to use racks always. So we can just move racks. -1, our trick value that gives us an 8-byte displacement. I mean, I would love to see the source code to ML64 to know why it makes it so difficult. If we put 0 in there, even lots of zeros, it won't ever give us 64 bits. It'll give us 32. Really, it's a stubborn little tool. Uh-huh. Comments wrong. But just to be neat, I want to put these comments here because it becomes a lot more clear what we're talking about. Okay, so there we go. Look at that. Okay, I don't know why. Oh yeah, I have the comment in here still. Okay, whatever. Double comment, no big deal. All right. Have I done this all correctly? You know where I'm most worried right now is this code. I'm almost certain this. When we're building the SCCs, I'm certain I've screwed this up. But if that's all I have screwed up, I'm really happy because it's pretty easy to fix. Maybe. But probably because I'll just go through this 20 lines with, some deep thinking going on, and I think I can just find it without even debugging it. Or I'll debug it last resort. Debugging it won't be as hard as actually debugging the machine we built before, the virtual machine. Although we could put print statements there. We could get print statements to work here if we want to. Since we know how to call lambdas now, we can do anything. That's like infinite power once you can call lambdas. We're going to leave the breakpoint there. It's not like we're expecting this to work anytime that soon. You know this is going to... A diabolically hard task like this, you're going to get stuck on every little thing. But the good news is that I know every little thing that I am going to get stuck on already, up front. So I've already said everything I'm going to get stuck on. One thing I don't like is the fact that these offsets are changing still. As I said, we want to stabilize this blueprint as fast as possible. Do not want to be changing this anymore. But if I see these kind of major issues, and I should have just worked this the first time. I knew about the RCX register being set with the standard function and then just calling operator parentheses. It's kind of like, I knew it, so why didn't I just do it? Well, it's just kind of a process here. I agree. I should have just gotten it right the first time around. And even now, there's no guarantee. Absolutely no guarantee. It's so difficult to get this stuff right the first time around. So 50, we're fine with that offset. I have to adjust all these offsets annoyingly enough. So, okay, so if we go to 86 around, of course, it won't be the case. Yeah, it will be the case. Counter. What's the next one we need to do? Is this one. This one, yeah. 6D now. This is where we've started changing stuff. So 6D and 77. But what we're going to have is now 6D is this one. That's right. That's the CX. But what we're going to get is a bunch of new offsets. We shouldn't do it that way because each one's going to have a different operator parentheses potentially based on which template specialization it was. Now, if they're all void ones, like with the sat, unsat, and the solution ones, they could probably share one. But this one won't. This one needs its like operand offs. All right, so this one needs its operate. Oh wait, 60. Okay, yeah, 77. Yeah, okay, it doesn't matter. B9, B8. Probably a lot of comments have gotten screwed up. Yeah, this is a B9. I know it's impossible to keep up with all this. B9. Okay. Yeah, CX will be B9. I don't know how many I've screwed up now with these comments. These comments aren't that important. Oh, I've screwed them all up. Face the facts. I don't like to have bad comments in here though, because it could potentially just make things more confusing. So, okay, so I fixed them all. We put this offset in. And I think that does it. Okay, so we do this next one, the start topo offset, and yeah, I don't want to do this again and again. I think I'm gonna start already fixing this. So yeah, let's do that because if we are gonna do this it's very hard to get it right. And I do want to make a process for the future. And so I should be thinking about the next program, not just this one. We're making this one work slowly but surely. It will take some hours to get it working, maybe. If I was really lucky, we can be done within an hour. It's possible. But you have to kind of get lucky because even after I get all of that stuff working, as I said, there's going to be some stuff in here. Actually, come to think of it though, it is pretty close. Maybe it won't take as long as I'm saying. Maybe I should just race for let's just get it done within the hour and then we'll go back and we'll start generalizing. But problem is sometimes you get lazy. You get lazy after you get the exciting solution done. You don't want to go back and just sit there and generalize. It's like, okay, I have it working already, whatever. But no, it's not whatever. It's so important to say, hey, this is percent index 1 plus 1. All right, so we call it the index offset. So what I'm doing here, okay, what I'm doing is putting a special percent in here, and I'm saying we're never going to use percent in a comment. And again, it's kind of confusing because I use this for my self-modifying code language, but I don't care. I mean, really, this is easy to parse. We're parsing a label starting at this offset of this instruction, and how many opcode bytes it should skip. But we'll not call it opcode bytes. Let's call it opcode sequences that we should skip. So actually, let's just say 2. Why not, right? Why not? Because we want to skip 2 sequences. 1, 2, and then here's the next thing. So what we want to do is we want to skip this, skip this. So what it'll find is when it does this, it'll see, oh, look, 1, 2, those are both bytes, and it'll know that it's at offset this plus, and it can keep track of the offset, and we don't care if it's multi-line, because when it's multi-line, there is no offset, so it just can keep adding to the offset. And so we will know the offset of each of these. Yeah, actually, let's do this. This is so easy, right? Then I don't have to waste time ever again with this stuff. So, okay, the count, this one we can just do counter offs percent 2. I think they're almost all percent 2. So, oh, this is going to be nice, actually. if it works, it just saves a ton of time in the future. Then I can change. I like it because it really is starting to get general. It shows that you're being a lot more thoughtful. Where's the next one that we need to fix? Some of these should already be fixed. Most of them should. So it gets towards this end part. I think it's start topo, yeah. Check same SCC. Okay, we're almost at the end here. Now this gets into the one that's like the special one, where we're doing this instruction here. And we'll put 3 in there. Now, ideally, it would actually write exactly this. It would still put +1, +1, +1, and I think we'll just make it do that. I don't see why we can't. Okay. So this one, this one, this one, this one, this one, and this one. And we're done. So we've got this unsat offset. Okay, unsat offset. These will all be 2. Because it's all move instructions. It's not like we're doing a compare instruction or something else. Only that one is a compare instruction. So since they're, oh, this is a relative address. So if we want to do it like this, I think we can use relative address. I think we already have that worked out. I'm not sure, but again, these are going to be the last details that we have to work out. I'm hoping though I got the code finally right, and like literally we're starting to get it close to working. Like we're going to actually be able to start getting nodes, calling nodes, to getting to the SCC code, getting to the final solution code. If it works, it'll be really satisfying, really amazing to see such a system actually going through. So we'll call this, well, we've got add solution offset, sat offset. Now we just need a different name. We were calling this what? OPP. Operation parentheses, or operator parentheses. Finishing these last ones off here. Okay, let's actually just manually do it for this one time only. But if we have to change it again, we're fixing the parsing code and we're going to just do it. Because to be honest, the system I'm using here, it's definitely doable. There's no doubt. We can get all this info. So where's start topo offset? We can look for those special comments. So here's start topo at db. Check same SCC offset. I guess we keep going on. Check same SCC is this compare instruction at 14F. Yeah, actually, maybe this can be done. I don't want to predict how long it's going to take, but it can be done maybe in an hour. But that's, again, it requires a lot of luck for that I just don't make mistakes along the way, and I'm able to troubleshoot them very quickly. At this point, though, I'm still filling in code. That's why I want to say that it can be done in about an hour after I get to that point where it's only troubleshooting left. Because that's when you know that you might be able to start burning through the the problems really quickly. And I was shocked when I got the last one done. I mean, the first virtual machine problem, where I already had it in Python, just translating it to C++ effectively took 8 hours. Although I did some other tasks too. And C++ is much slower, so I mean, it's not that surprising, but and it took me a full 8 hours to just write pseudocode. Uh, it invent like a pseudocode high-level language and get most of the assembly done. I couldn't finish it. It was just like too tired, too exhausted from doing this. Okay, so this, it's almost fun to just run it and try it. I mean, again, we can go after the automatic generation of this. I think it's easy now. I think it's about 10-minute job, and it's worth doing. Okay, we're still generating blueprints here. Is this? Yeah, it's okay. The windows are all showing properly, which is nice. Doesn't always do that. Should though. It should be able to figure out which is the little console display window. All right, let's just see what happens here. Okay. So we're going into the assembly code, and here we're calling racks here. Oh well, yeah. I mean, uh of course, I never tried to deal with that operator parentheses problem. Now, we can deal with that out here. Isn't that nice, right? Because it's going to be the same in the blueprint for all the nodes. We can just fix it once. So what we can say here, again, we can use a void pointer maybe. I mean, it doesn't, at the end of the day, it's just a pointer. So the first one is going to be this one. I mean, ideally what we could do is say, in an ideal world, we could just say, give me the address of that operator. Unfortunately, we're not living in that ideal world here because it's definitely not working. Okay. The problem is if it's never going to be a portable solution if we can't trick it into giving us what we want. I know it's going to fight me on this. You know, of course, we were reading about how GCC has this mechanism. So all three of these pointers are going to point to the same function. Oh. Oh, wow. It's a function pointer. Wow. You know why I'm pausing here? Why does it say that it wants to convert it to a void star star? Oh, because I'm missing a parenthesis. Oh, gosh. Oh, that's awesome. So this is going to work and hopefully be portable. Okay, void star is what I expected, and we can just cast that one out of the park here. Maybe. Wow. Done. No. Why not? All right, this is weird because actually now. Okay, I see that there's some real problems here with technical details. Apparently, some compilers have 20-byte uh, function pointers and weird stuff for the calls. In other words, they're maybe not a straightforward way to call some functions. But I'm gonna not say we're trying to be compatible, maybe perfectly to the C language, but we're gonna deal practically with Windows, Linux, 64-bit and 32-bit in simple, normal console applications situations. Uh, in 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 terms of like every possible scenario, yes, you'll have to design custom solutions in every single environment. There's no doubt. But these two, the solutions for Windows and Linux will be sufficient that you'll be able to get to most environments reasonably quickly, and then yes, you'll have some time dealing with technical details. Let's see about getting uh, casting a function pointer to void star. Ah. So some people are recommending that you use this trick. Here's the tricky route is you go through this route, and if it won't let you go through that route, you make a union. Oh, that route worked. Do we even need the void star cast at this point? Yes, we do. Wow. So the one idea is you could make a union with just casting a function pointer to another type of a function pointer. Again, though, you're going to find that if because a function pointer is not necessarily a pointer in a traditional sense, it's not guaranteed. So yeah, you do have that issue. Um, Again, I know the details of all the semantics, and I think this will. Oh, it's not working still. That's not good. Why isn't it working? You gotta be joking. Is it because it's a template function? Mm-hmm. I don't think a reinterpret cast will work. Somebody said use a reinterpret cast. Seems like the wrong direction for this. All right, well, I have to figure this out. This is a stumbling point until I can figure it out. Yeah, we need a data reference. Now, some people are saying avoid star ampersand. Again, I just am skeptical that any of these techniques will work. Of course, it's not going to work. Yeah, this is an architectural issue where data and instruction pointers are considered physically different things and such. So, uh, of course, in our architecture here, they can just be pointers, but there's differences we see with RIP relative addressing. Uh, one is relative, one can be absolute, or this and that. So uh, there are a lot of details that are going on here. Yeah, again, I highly doubt this is going to work. All right. No matter how hard I torture the compiler here, it doesn't want to comply. Okay, what about another trick? Let's use the trick that I see here. No way. No way. No way that worked. Yeah, again, I don't know if any of this works. We're just playing games here for now. But it might. But it might. F void pointer, let's call it. I don't know. Wow. That's really cool. Yeah, whoever came up with this, cheers. That is awesome. Again, who knows if this is portable at all? Void pointer here. We can set all these the same. We know they're all the same. Wow. If it actually works, it would be amazing. I'm kind of scared. Whoa. Whoa. 1F000. Oh my gosh. Wow, the stack is totally so messed up right now. Oh. Well, that was a great way to try to blow up the system here, because that really made a mess. But it means that we're calling something. I don't know what we're calling, but we're calling something. Let's see, a little walk. Take a little walk here. Okay, we're in our code now. Okay, we see it. Oh yeah, look at this. Look at this. Operator parentheses. It knows. It knows it. Okay, what happens? I call operator parentheses. It jumps. Okay. Oh, this is just nasty stuff right here. What's the ESP? The RSP? Let's debug window registers. So we want to make sure the RSP was 16 byte aligned and all these types of details were properly addressed. It's not aligned. Probably doesn't matter here, but we'll see. Because right now it's 16 byte line, but it should actually have the return address and be 8 byte line. Now, we did call this, right? So yeah, that's interesting. Oh, but we popped the return address. Okay, we need to fix that. Oh, yeah, there we go. Another blueprint change. So when we pop the return address, we don't peak. We need to add ESP8. We need, again, this is, oh, of course it won't work though. The stack won't empty and you'll eventually crash or something for this, but no big deal. Oh, look, we get the source code to this. So we actually want to like wait for it to actually call our function. If underscore empty bad function call. Good, it didn't jump to bad function call. Get impl do call. Look at that. Forward, it's doing its forwarding. So now it should actually go to the code for our lambda. Well, almost. It's calling it to call. Yeah. Hey, who knows when it's going to get there? Okay. Call. How many different invoker? It's going to keep going here. Man, STL is a monster when you want to debug. Yeah, in fact, we don't know how far it got because actually, as far as we know, this works. Invoke lambda. Finally, it's got our lambda in there somewhere. Wow. So it really is working. Oh. Okay, call lambda operator parentheses. That's what we were waiting for. That's what the standard function is finally wrapping. And again, in a release build, oh yeah, look at this. Look at this. What's index? What's index? Index is the RCX register. RCX? No, the RDX. Oh, what am I talking about? RCX is the, yeah, it's 1. Index is 1. Okay, that's fine. That's the wow. It's working. I don't have anything to say. This is absolutely working. And so the rax is set to the pointer. Look at that. Set to the next code pointer that we want to call. Let's see if this actually works. Wow. That's awesome. That's awesome. We got the pointer. Wow. Wow, wow, wow. We can call lambdas. Successful proof of concept. We can call lambdas in C. No problem. What's the stack pointer? Yeah, it's messed up, but we know why. We know that after pop, you needed to add back to the stack. But when you change it to peak, you're gonna have to like deal with that issue of you need either pop add or peak, and we will figure out how to do that. Actually, I think that's gonna make things a lot easier. Maybe it'll make things different. That's all. It's easy though to fix. Okay, what do we have here? Not equal. So let's see if the rax is right here. Yes, it is. Look at that, the next one. And it's going to modify this instruction. Again, if it modified it, we'd have to like refresh the window. I don't know if it's going to show that this was modified. Oh, that's so cool. That's so cool. All right, I'm going to abort this because we've got the first part of it working actually. So we are like nearly to debugging, but again, there's still mistakes in here. One example of a mistake is this pop instruction. Can't just do that. Because if you want to pop, you need to add RSP8. The question is how many bytes? The question is, can we fix this without mucking with anything? and keep it as 7 bytes, because that's how I think that's how many bytes we needed for the peak instruction. And if that's right, then we're in good shape here. So we look at the listing file and we see what happens when I put that in here. So, ooh. So actually, it's 5 bytes versus 5 bytes. I think we just do 2 move instructions and don't try to be too fancy here, because honestly, that's about as good as you get. What else are we going to do? It doesn't make sense to... yeah, I don't see any better thing to do here. Oh, popping the racks won't work. Oh, that's even worse, because we subtracted. I'm almost thinking, yeah, actually, but we can't. We can't do this adjustment. It's this actually it's very tricky. We have to be very careful with these RSP adjustments, so because we can't ever corrupt the stack. We know things are going to break if we do it. So we do need an add RSP8 here. And we need to be very careful, because if we put a return here, of course, we're okay. We don't need to ever play with the stack. And if we leave this sub RSP in, if it gets down to any of these calls back to C code, we have to make sure we're adjusted again. And this is where things are going to get a bit tricky, but we don't need this anymore. So that's ancient history. So we find where we reference the peak ret lobe. And what we're saying is move racks ESP, which is peak. Oh, that won't work either, though. Oh, man. Okay, this is just complicated. The reason we can't move the ESP is we've subtracted from the ESP. So we actually want ESP, or RSP, I should say. So we want RSP plus 8. So we want move racks RSP plus 8, I suppose. Oh, this is going to get really, really tricky really fast. This is going to get really tricky, because it means if we peak or pop, we not only have to worry about the subtraction, but we are going to need to fix the adding to the RSP as well. Well, no, actually, if we peak, it means we're leaving it on the stack. So we'll just leave an extra 8. Actually, no, we can adjust that here. When we pop, we can pop twice. Actually, we won't pop. We'll just... Oh, yeah, this is going to keep changing then. So we add ESP8, or RSP. Yeah, it's exactly right. So we add RSP8 over there, too. Because we're going to be getting 16 bytes at a time off the stack. This is the tricky part here. And as I said, we just have to do it. I mean, there's no choice. Tricky, but not the end of the world. Definitely can be solved. So now we see that if we're going to peek at the stack, we don't want to like add back. We want to keep it aligned to the 10 hex bytes. So what I want to do is just quickly grab the opcodes for this. Okay. Oh, it's still, it's the same, isn't it? It's absolutely the same. No, it's not. Oh, this was ESP. That was wrong. Oh. That's wrong. This is such a concern, though. This is such a concern, because we can't just add to the RSP here unless it didn't happen here. It's like, again, we want to leave it... I don't know. It probably doesn't even matter. I think we just take all of these add subtracts out. I don't know. It's a convention, though, for going back into C. Because we go back into C code, I just don't know. To be perfectly compatible, we should follow the guidelines. Okay, move racks. Wait a second. Here. So we're going to use rip relative addressing. We're going to peek ret loc. And what we want to put at peek ret loc now is this in in the right endian order. So we can just do that as 0, 24, 44, 8b, 48. We want to say it's a D word pointer. Is any of this compatible? Like, are any of the bytes the same? I don't think so. 58, 48, 83, C408. The 08 is the same. How awesome is that? So here we're adding RSP8. Here we're using RSP plus 8 as an offset and a move instruction, but we only need to change 4 bytes. Yes, that is so lucky. That is really, really lucky. You never get that lucky. That's so cool, actually. That is cool. So we're going to do that. Okay, so we've solved this. As I said, we don't want to delay misery since we're seeing how slow it is to do some of this stuff. But the fact that we solved lambdas is huge. I'll tell you, that is really, really huge. So one idea here is the problem is we're calling lambdas all over the place here. And of course we want the ESP, RSP to be fixed here. We know that the call to sat, if it actually calls sat, will never... Anyways, to cut a long story short, what we're going to do is we're going to... This do start topo, it comes after. Remember, it comes after the last... actually, where does it come? Oh, we don't actually call it yet, do we? But it's going to have to be called at some point. It's like the code that comes after. Mm-hmm. It's yeah. Well, technically, there should be another like lambda here or something. But we're gonna just need to call. Don't forget to call it, right? We know it's... Where do we put it? At the start or at the finish? So we're gonna mem copy it somewhere. So we mem copy jump topo to the start of the code block. So it's at the start of the code block. So we can just say p code block. That won't work because I need to like... put another parenthesis, I think. So yeah, we can just jump to the beginning of the code block here. And that would satisfy... We're probably getting rid of this for each. There's no way this is going to work. You think about it, this for each is a total disaster because we need the stack to be totally controlled. We cannot allow this type of thing to happen, I guess. Yeah, absolutely. Like, we could put this in the blueprint. Probably we have almost no choice but to do this as part of the blueprint. And I don't see why we don't, because it's easy. It's just call statements. It's too easy. Call statements, and then we can actually fix the rest of this problem here. So basically the end of all the call statements, actually we're starting to make it closer to the other model. I really like that. Okay, low link load, add RSP. That's a different problem right there because it's been after a call instruction. There's no call instructions here. The only call would have been to this one. Eventually jumps to sat, which would return to the caller. Oh, this little 8-byte adjustment here is just so much more tricky than you think it could be. So what I'm going to argue is that we could do like this. I'm almost coming around 360 to saying to just forget about the adjustment, because if we jump to a function, yeah, just forget about it. In fact, we're right, because if we call a function, that's a different story. When you call the function, you need to be 8-byte aligned so that it realigns to the 10 bytes hex bytes. But when we're jumping to the function, we actually already want to stay 8-byte aligned. So here we don't want to like go back to 16-byte alignment so that the call makes it back to 8 alignment. We don't care anymore. We're jumping. And in that jump case, we actually want to stay like this. So, okay, I'm willing to say this is correct. Now, I'm willing to say that this is going to crash if it ever goes back into the for each lambda here, because we've totally screwed the stack up. We can't do this. This will never work. What we should do is put a bunch of call instructions in here. So what we should do is just, we could even do it with relative addresses. It really doesn't matter, but we need to move and call, move and call, move and call. So we need like for each node. For each node we should do that, and then we should just call this at the beginning. And we will have to like do a little bit more calculations for sure. But we avoid any problems because then we just have our call chain absolutely perfect. The only problem I see remaining is that this add RSP only needs to happen if it peaked. Wait a second. The problem is, yeah, no matter what we do here, if we're gonna like mix and match, whether we're 8-byte aligned or not, we could always detect it, but we don't want to go into that. No, we want to do this correctly right from the get-go. So there's two cases to think about. If it popped the argument, well, it's already added to the RSP, so we definitely don't want to do anything. The stack has already been corrected. Otherwise, if it peaked, we want to leave it on the stack. The question is, do we want to leave it on the stack with 8 more bytes? And the answer is yes, because we don't want to, it'd just be too confusing. So we do want to leave these 8 bytes on the stack if we peak. It's totally annoying, but somehow this instruction, probably it's a 4-byte instruction. The problem is if we don't fix this type of stuff right up front, you're just asking for trouble. The easy thing to do is either use an EB02 to skip 2 bytes and some garbage code here, or put 90s in here. You just no-op out the whole thing. Excuse me for 1 second. And so, I mean, this is like the strategy here. I think I'm going to make a coffee. I need some more energy here. Going deep into these issues is not easy. Coffee almost ready. All right, so I get to get back to this task here. The task is now to figure out what we're going to do about this add RSPs. Absolutely something that would have to be adjusted. Again, we don't do the adjustment correctly either, so I mean, we're just asking for trouble in a couple places still. And all of these, like, again, it's going to start to get a little painful to keep walking through the assembly. It's another thing. We're going to have to regenerate this code too. So we're going to fix that as well. We're going to start using our tags and generate the offsets that need to be relocated. So I think, wait, coffee maker just finished. Tea maker. Okay. So the thing to do is to try to solve all these issues before recompiling. Again, to just minimize the amount of times we have to do this. I think we want to start looking into even more details now to make sure that we're going to get this done. I want it done, within, like, let's say 3 hours at the absolute maximum. I want this whole thing done and working 100% with, like, some generality for regenerating code and all that. The this instruction is definitely suspect. It's like one of these details of 64-bit assembly. Just gonna put a label for it, and we're just gonna we're just gonna nop it out, I guess, for now. I don't know. There's different ways we could do it. So yeah, this was clever. The other one we're gonna have to do then is this one. Or jump $+2. So 2 choices. And we're just going to move a double word. I think this looks nice for now. Of course, it's not very hard to put. Of course, it would be like 0000 or 9090 to make the code stay intact. Actually, this is even more elegant because we don't have any dead code. We don't have any like garbage partial fragments of code anymore. We could again, so we could even say like EB029090 to be more nice about not having dead garbage code. Doesn't matter. It's not reachable. Oh, is this EB04? No, it's EB02. I'm pretty sure. So the way forward then is okay. So we've done that, but the problem is this is wrong as well, because this is doing the current node, not the future node. But we have the pointer to the future node, right? So actually, this is a relative address, and actually the nice thing is we can just use it. It's just racks. Actually, that's really cool if that works. All right. Are there any other details we want to address that we think things are going to go wrong? Obviously, it's able to now call nodes in this scheme. Now when we debug, we can just step over this call racks. And we know this address will be pushed on the stack. So there were some other questions I was kind of saying, okay, let's check what we do here. Compare racks. Okay, racks now should be the return value. Fine. With the low link. It's going to be the low link, which will either be the index returned up here, or it's going to be the low link returned down below. If all goes right here, we have the low link. So the problem, though, with stepping over call racks, though, this is going to be a real pain to debug. One thing is to put a breakpoint in our little lambdas to just kind of break there and then just walk out, because the exit is faster than the entry into it. Because we're going to want to like see it get to the next node, and we'd have to set breakpoints at all the nodes, and they're all changing constantly. This is definitely a tricky type of an issue. Yeah, so we're getting somewhere, though. We really are getting somewhere. This is... Let's just verify what we're doing so that we know that it's working. Do I even need this offset in here? I'm pretty sure that it's the offset keyword is maybe to be portable, but we'll need to put it everywhere then or something. I mean, we should be consistent with it. So, okay, so we do that. We move it into the ECX. Even though we're just going to use the CX register here. And we move this to check SCC log. Oh yeah, that was because check SCC log is this 9090. It's a no op, and we want to make it say jump to. Well, we can check if that works. I mean, this is just a simple jump calculation. Yeah. Again, why we had to use ECX here, it's just because the compiler isn't smart enough to know that this is 1 byte, or 2 bytes total. This should be just 2 bytes, but if I do it, it'll CX, it won't work, so. Again, this is like a problem with the assembler, not with the, not theoretically here. Maybe a different assembler would actually work. But since it's not a huge, important issue, as I'm saying, we could hard code this with DB. If we want to fix it, we could just do DB66, DB9B9, and then this immediate value. But again, it seems like it wants this to be a 32-bit value, not. So even if we did that, we'd have to do DW, and I'm not sure if it would work. We could even try it. Oh, that works. It's so weird. Oops. CX doesn't work. but that does work. So it would be something like db66, comma b9. Yeah. Uh-oh. I mean, so just to continue the comment here, if we want, we could do that as well. So the assembler will somehow allow the 16-bit argument here. But here it just wants it to be 32 bits. I don't know, because somehow it sees this pointer difference and says, hey, no, this is 32 bits. Even though I'm saying, no, it's definitely going to be a small value. It's going to be a byte shifted left 8. Yeah, I kind of wonder if there's a way we could, truncate it maybe? Would that work? No. No. No, no matter what, no matter what I try here, it wants to be very stubborn about this, huh? All right, it doesn't matter. We'll just leave it as the ECX. Okay, it's just gonna jump to counter loc. Okay, it's fine, done. Unstack loc. Okay, fine. This has been adjusted already, presumably correctly. We get here. Okay, this push instruction, is this right? Like, as I say, I want to kind of finish this all off right now. Well, we know for sure it's not right because we want to be aligned here. So yeah, okay, so again, we're like dealing with details here, but they're important details. Here we have to add RSP8 and pop at the same time. So we're always trying to keep this 16-byte consistency going so that we can be compatible for calling back to C functions. That's a lot of work for dealing with that, like, minutia type of thing. Okay, so far I'm satisfied with that we're doing everything kind of correctly here. Of course, as I said, we're going to need something to fix this as well. We're going to need to expand this into like its own little blueprint area. But it's a very easy blueprint. It'll just be some pointers. And then we don't need a for each anymore. We'll just make one call, and that's it. It's going to start executing this code, and it will return back when it finishes all of it. And the stack pointer better be the same as when it started. And if that happens, wow, the job is finished. And presumably we have the solution to the 2-sat equation. All right, let's see what the next thing to do with this is. Okay, so call loc P1 is here. Okay, now we've got a problem because actually what we want to do here, we need to know the address. We need to relocate this effectively to our node address. There's two ways to fix something like this. One, of course, is to add fix-ups, but ideally we don't want to add fix-ups, but I don't see that there's a way around it. We cannot push a relative address on the stack. Yeah, this is a 3-byte instruction, so I was saying like, okay, the difference, but this is not necessarily a good thing here. The problem is we need the rip value. So I'm searching for how to get the rip register to get the instruction pointer value. Usually it's implied that you're doing relative addressing, but here we don't want to imply anything, because when you call a function, it actually puts the real rip value, not a relative value. One trick we could do is do a little call. But if we do a call, it'll give the wrong location. But I think it's exactly what we're going to do. This I know won't work. Unless I know my own node's address. The problem is I don't, because nothing, if it's not on the stack, I mean, we know the caller's address, it's on the stack. Well, we may know it, but not really, because we may have popped it and all that stuff. But we don't care about the caller, or what called us. We care about this function's own instruction pointer. There's a question, is there a way to do it with... like load effective address or something like that? Yeah, it's actually, to me, there's like 2 ways to do it. I don't know if that works. I'm pretty sure this doesn't work. Maybe we should take a look at it, but again, we're going to need to fix it so it can generate the blueprint better. Then, oh, I see we have add RSP. Okay, so that's fine. Call loc p1 minus node adder loc is what we're subtracting. Well, that's right, actually. That's going to give us the original node address. Because again, that's this will subtract some amount of bytes to get us back to the top of the node. Then we add this value. Actually, this looks pretty good. And we move to RCX +1 because this is pointing to a jump. Oh, this is pointing to a move instruction, not the jump. So yeah, that's fine. Then we ink the racks. Why do we ink the racks? Because we want the next byte, I guess, of this. Why do we ink the racks here? So we look here. I don't know why we ink racks. I think we need to increment it twice or add 2. So node adder set loc is where we're setting a symbolic value to see which SCC each node's in, so we can have a way of comparing it with its counterpart node. But it's also the address we want to jump to. So we set it to the address we want to jump to. Yeah. Oh. We need 2 of these instructions here. Now we're going to assign it. What do I load it? Node adder loc minus $. That doesn't make any sense, does it? Okay, so we should fix that. So we want to actually put in... Okay, I'm glad I noticed this. we want to put in the current node address. Yeah, it's the same issue, isn't it? It's absolutely the same issue. We want this to be the RIP address. Load effective address is the theory that this might work, though. So if that gets us the current node's address, I have to think about it, but it might need a little adjustment, like another -3 or something for the load effective address bytes, but this actually potentially could be right. Oh, we have successor size here, and we don't have this actually included. Okay, I don't know why this is like this. I'm just going to do this for now. And yeah, we can leave this meta tag in, and we're going to actually define it in here. This is all the tricky stuff. The thing is, I want to kind of redo some of the stuff that I know is going to be a problem later. There's just no reason to not start fixing these things. The successor size offset is another blueprint fix. So we just put here a long pointer. Or we actually, oh yeah, why don't we, oh, this is even better. Why don't we just make index size t? And we do the same thing here. This will be size t. I was just thinking about that. So we can say successor size, and we're done. Yeah, this is a pointer to index, while this one is actually not a pointer. It's just an immediate data value. I mean, we could use move with sign extension if we want to make it 32 bits. Just thinking we'll just make everything kind of 32 or 64 consistently. If we want, we could make some of the 64 stuff use 32 bits where you know it's totally unrealistic to put a 64. You're not going to have that many nodes in a graph. All right, so I think this is going to work now. All right. The problem is we don't actually parse our meta tags out. So let's do the meta tag parser. Okay. What we have is our line parser here. And the first thing is the offset. I think we get the offset here. Yeah, we do get the offset. So this is a single byte one with a little detail about the prefix. This one is a now we can just be nice about it here. Oops. So we're going to track the offset. I mean, actually, really what we should say is b.size divided by 2. Again, rounding down will work perfectly there. Same here. Works perfectly. And it works perfectly here as well. And this is just ignored. Perfect. Okay, so we've got the current offset, and now what we can look for is in this string, we're going to look for comment. And if it's not equal to line end, then there is a comment here. And we can get that comment oh wait, it doesn't return. What does it return? It returns like a line end pause. So end pause is probably -1, means it didn't find it. So otherwise, we probably should just save it. Returns a size t. So if it finds a semicolon, we're just going to parse the semicolon. So we'll just take the substring of the rest of the line. I guess kind of we want to trim it. Is there a trim? I don't really care, because we can actually save the comment. So okay, we've got the comment saved, but we actually don't necessarily want all of that comment to be there, because we want to now check again. So we'll make an, how do we want to do this? We're going to probably want an array here. Or a vector. So we'll make a vector of strings, offset. Okay, so we've got our offset vector, and what we'll do is the comments, if we're going to use them, we'll just put them in the same line as C comments. And the offsets we're going to actually look for again. So what we probably need is we can actually get rid of them from the comment string, because we don't want them there. We'll just assume to the end of the line. We'll assume % to the end of the line type of scenario. We'll assume that the syntax here is not an issue. It's easy to write those little meta tags for now. There's a better, more elegant way to do it. But I think this is this is the right way to go here. So the way I'm going to do this then is comment.find %. I'm just going to make that C pause again. Comment, now it'll be, I don't know. Doesn't matter, it's an offset now. So, if this is not equal to comment.endPause. I mean, again, the endPause is just a constant. Actually, we could do, I think it's standard string endPause. Maybe that's the cleaner way to do it. It really doesn't matter though. It's at the end of the day. I think the constant -1 will be compiled into there. So if there's a % sign there, now we're going to use this offset which, by the way, has been continuously being calculated. It's either gotten at the start of a new instruction, or it's wherever we're emitting bytes, we're adding to it anyways. So we can count the number of offsets. The problem is counting the number of offsets is a little tricky. Because by the time we see this, we don't know yet. That actually, it's kind of an issue, right? So we don't know the offset yet, so we'll have to figure it out. I have a perfect way to solve that, though. Yeah, it'll be really elegant if we do this correctly. So what we're going to want to parse out, though, is the name and the number of offset increments we are waiting for. I'll just do something like this, and maybe -1, maybe a size t. So here we'll do, we want to do two things. We kind of want to split the comment string. So the comment string needs to be substringed eventually too. So actually, first we'll set offset equals comment.substring, and it'll be the substring starting the character after the %. So we'll do the usual C++ one. And then we'll take that and get rid of it from the comment string. So we'll actually say comment equals comment.substr. 0, but C pause. I think that's right. We don't want +1, we want the percentage gone. So I mean, that actually looks perfect. Then we can, again, keep parsing this offset string. We'll just, at this point, we're just going to assume it's a valid string. We can just keep reusing cpause. Cert. So now we can get the next value. And we'll just assume it's to the end of the string. We'll assume it's %, %, end of string, /00, something like that. Let's just put a comment here saying what we're doing. And then it'll be actually, offset increments. And there we go. What can we do here? Well, we're gonna. This is where, okay, we need to somehow parse a number out of this thing and all that. It's silly. In fact, we might as well just like say, okay, we know the substring we want, but we don't know necessarily the count, but we know we want to take the last byte off. We can just walk through in the debugger. This is kind of a tedious little tricky code here, but this is most of it. Then here we only have to do a couple things: add to a vector, print out the vector, and then we have a way of getting all our offsets right into the C code. And that really is so cool, because that means doing more self-modifying code in the future will become just that much easier using a tool like this. And this can be retooled or readapted. The code isn't the strongest, parsing code, but it's decent. It shows that if you need to get a job done, you can, in a general way, so you can reuse it and recode stuff, you can. So we want to take this substr of C++1. Somehow we're going to want to trim the end of it. How do we do that? Something like that should off by 1 here, because we want to just take off the last byte. So relative to the offset we're starting with, I'm probably off by 1 there. But then we can actually use the usual tricks with STL and just make a standard string stream. That'll give us the increments. And in fact, actually, since we might as well just not even save this, we'll just make the string directly. And finally, we just need to trim off, based off the cpos, we can just say comment offset equals offset.substr cpos 0 cpos. See if this works. I shouldn't have named it that. Reused a name that we already used, so that needs to be fixed. Okay. Call the parse code. And we're going to make this work. Uh-oh. Just initialize it out here so we don't get any of this type of nonsense. Of course, there's some prelude code that is going to, be parsing, and it needs to have some initial value here. Oh, never finds it. Oh, because I did this too late. What am I doing? Okay, here's our comment. Move racks. Let's see if it gets it. Comment is move racks. Okay, great. It doesn't find a percent. Just found a comment. Okay, that's perfect. Where's the first comment with a percent? Let's see where it happens. Okay, found one with a percent. Yeah. Percent index off percent. Okay, so let's see what happens. Oh. It helps to put parentheses into the code. I know I'm taking too much time on this, but this is, again, it's like one of those, if you're lazy and don't do it, you don't really get anything for the future. You just have done one task. And I'll waste more time doing this task. Okay, good, that parsed correct. Comment, is it gonna delete that? Yeah, it did. cpos is 9, okay. It's not 0. It got 2, huh? Okay, it's working perfectly. So what we can do now is look at this increments uh, variable, and we can start decrementing it, and we can record the offset when it gets to 0. So what we need to do is make sure only when it's 0 do we record. So we need this to be -1 if there isn't something being asked for. Now, if it was multi-line, that could really be a problem. But what we could do is it could always be initialized to -1, and then if it goes negative, we could just keep letting it go -2, -3. We could just always decrement, and that's what I think we're going to do here. Or we could say if it's not -1, decrement it. It doesn't matter. So this is going to be increments minus minus. Yeah, this is nice. This one we don't do anything. And so now if increments equals 0, then we add to our vector finally. Then we're ready to go here. We do need to build a string though. Offset vector. Okay, actually increments minus minus, not particularly useful to build that string that I'm talking about if we want to be elegant. So when we do this, we want to add +2 or +4 or +8 or whatever it is. Oh, we don't even do 4 byte. Well, we should do those as well, but it doesn't matter. We don't have them yet, but we should do short words as well. Okay, this offset vector dot push back. Let's just put offster, and then at the very end, let's just say, I like to overuse and overabuse standard for each. So we'll go through the offset vector and we'll just print them out. I mean, there's nothing to this. However, these strings need to be built. We have a choice if we want to build them here, or you might as well just build them here. So this is actually going to be what? What are we calling them here? We're going to just use these as a prototype. So this is what we want. If we know what we want, then just do what we want. Heck, we could even put 2 tabs here just for, /t/t. I don't know what standard tab is. I know it's a 0-9 character. I guess we could just see out it as a character. Or a string. A string is /t/t. That's perfect. So, but in this case, we're going to need like this kind of a string. All right, so greater than, like we'll just say increment string, greater than semicolon. Could put the new line there, but we don't need to. Actually, we could just make one big string, but so we need the increment string. That's easy. Maybe not easy. I'm assuming this deals with the memory buffering and everything for us. In fact, we might as well just not uh, even store offset string. We might as well just store the stream, and then we can just add this part on. Oh no, we'll need the offset. Oh, the offset is the current offset, isn't it? Yeah, it is actually, because if we're in the middle of an instruction or these multi-line, it wouldn't even matter. So actually, yeah, we might as well pre-build this, and then we can just add the increment string. Or actually, we don't need to add the increment string. We can just add to this O string. We can just add the semicolon. I like that. Again, this is just like thinking about how to do things correctly here. Yeah, there's some technical details here that are not going to be perfect, but okay. I think we're getting there. Then the last thing to do is to just say if it's greater than 0, right? So if it's 0 already, yeah, we don't need to do anything, so that's fine. Actually, we can still decrement it. It's kind of sloppy. I don't really like this that much, but technically this should be greater than or equal or 0, and this one should be greater than 0. When it's equal to 0, actually we can just fix that later. Let's just do greater than or equal to 0 and make this as simple as possible. So it'll never be 0, because we'll never initialize it to 0, and if it ever hits 0, we'll immediately just subtract 1 from it again down here. I'm going to fix this as well, just put some tabs in. So it looks better when I copy and paste it. And I think that's it. We just need to do this everywhere consistently. And we need to just say OS less than what is this, +1. For now, I'm just going to hard code it. Okay, I won't. Well, it's going to make the code look longer, but it's a nicer description. Although, again, if it's supposed to be a pointer size, then it won't exactly be a nice description. This code is getting long. What are the odds that I got it all right? Not good. Wow. Wow. Okay. Well, this needs to be this. This needs to be offset. Now, it may not zero pad them and do stuff like I like it to be. Yeah, there it is. Okay. Ooh. Wow. So it works. Awesome. Okay, so this solves a technical issue. It doesn't, but it tries to. Okay, let's check the 3 byte one. Yeah, man, it works really good, surprisingly. But these aren't hex. Oh, they are hex. But then why are the offsets wrong? It's just wrong. 2A? 50 for counter offset? 50 for counter offset is right. 82? So the only problem right now is the offsets are wrong. Oh yeah, it could be. So we've got like this little issue here that the offset is being gotten here, but we're building the string here, so we have to kind of make a decision on this. Yeah, the problem is we need to like start trimming the line, but we don't want to find that tab and get rid of everything, but we don't want to find that tab and get rid of everything. So, okay, so it's a detail, but it's an important one. Put it right back up where it was before. All right, so, okay, the way we'll deal with that then is to save a copy of line, I guess. Oh, actually, the way we deal with it is by breaking the code up a little bit. That's clever. I mean, yeah, it's maybe a little less, because the comment will just be empty. Yeah, we have to do an extra comment find that we wouldn't have to do if there's no comment, or an extra find for percent on an empty comment. This type of stuff doesn't matter. Bottom line is we've got the comments saved, so so that we can trim line. Think this will work. I hope. Awesome, because then I can start doing. Yeah. That's beautiful. I don't know, but there's a way with STL to zero pad the output. Set width. I see there's a set width, but I think that's going to pad with spaces. Oh, set fill. Okay, I see. Well, I'm going to look at the standard example here. Set width. I think you probably need to use. Is there an example? I thought there was supposed to be an example here. 0 fill. Wait, I just saw it. I found a website. Okay, how to pad with leading zeros. Ugh. Okay, this is a stupid website. I just want to copy and paste the code. I don't even want to think about it. This is too basic of a task. Seriously. I'm not used to use. I like scanf and printf more than this stuff, but I figure it might as there's always a good time to just flush out the STL stuff. Man, seriously, I can't find one example to do such a basic task. Okay, there it is. Yeah, finally. Internal, arrange for padding to occur after the sign but before the remainder of the number. We don't care about that. There's no sign here. They're all positive numbers. So the rest is set fill and set width. So apparently we're going to have to tell it the width is the size of a double word times 2. If we want to be technically right, that's actually, instead of 8, actually, don't I already muck up my code with this? That's really the calculation going on here. This is really the size of a unsigned long times 2. This is the size of, again, this is just sloppy stuff to leave in. And this is the size of byte times 2. Size of byte. It describes like what we're parsing in a beautiful way, and that's what we want to do. Again, we're saying it's twice as much because it's hexadecimal, and that's fine. Could we describe it even more? Yeah, but it's close enough. So the last thing I said was this little detail here. Not just hex, but set the width to. Yeah, since we're indexing this array, again, it's a size t. We could use u long long, but it's totally unnecessary for printing the C code. Yeah. So apparently we need I/O manipulation. Yeah, I don't use those functions too much, but you should get used to them. Definitely, I mean, this is like, again, actually, that was probably just a waste of time. But okay, we've got all the constants now. Really like that. Let's check if we really got this, because now we can actually, we're getting to the point where we could automatically generate assembly code. We're really getting powerful here. Using the assembler and a special blueprint and some kind of blueprint builder. We're getting to the point where we can keep automating more and more and more of this. Oh, I wanted uppercase. Well, I don't care. I'm not going to care about that detail. So 50, 60, 0, 77. Look at that. Start top offs, successor size offs, check same SCC offs, unsat offs. Unsat. Hop offs. Solution offs. Yeah. Why not? Why not? I accept that. And as far as copying and pasting all this code, yeah, let's do it. Oh, and look, we got the 2 tabs there. Now we need to drop now a little bit more code. I almost wish we had like a way to insert a new line on a proc or an end proc. So yeah, that's the only problem I've got here is we should also track procedures. Again, that's the next step, but I didn't do it yet. So, okay, there's a call instruction. That must be this here. Oh, this is the jump instruction. This is a move. This is the call, and this is the move. So we start here. All right. Whew. It's taking a while. But look how good this is. It's even formatted. Uh-oh, why did we get... Oh, I see. Unfortunately, the tabs are not copying and pasting right. Maybe I should put 1 tab in instead of 2. Well, next go here. You just change that to 1 tab. Actually, how come it looks good in the other place? Well, I don't know. Okay. Yeah, I can't explain why it looks good in the... Oh, it doesn't. It just somehow copy and pasted incorrectly. Okay, whatever. Could put 4 spaces. Let's take a look at how we can finish this job now. This isn't going to work. We already said this is a bad idea. And we said that this is a good idea. But it's only a good idea if we make it work first. And so we have like another little blueprinty type thing going on. It won't be the same as this one. And then jump topo. And what we were saying about the stack is it just needs to stay partially correct, and it only needs to be corrected for the call instruction. And so that's easy as that. And then we just hope that we somehow leave the stack, because everything crashes if the stack is messed up. That's guaranteed. So what we do is this. I kind of feel like, because this is a singleton instruction, we kind of want to break these into 2 different arrays here. We do not want this to be part of jump topo. We want this to be call blueprint. So there we go. Now we are talking about something here. So actually, to be correct, because we're probably going to end up regenerating this some more, so we can just I don't know what to call it. Start to sat. So what should we do here? Again, we technically even want to name the functions. Okay, if we come back to generate again, we're going to keep fixing this. So I can just literally copy and paste all of this, and that's it. It'll just literally be a copy paste job from now on into the future. We're never going to do multiple copy and paste. I'm literally going to take this. It's going to generate C code. It's going to take the assembler output, generate valid C code that I can just like even dump into a C file. And we will have like an automation process where we can actually like literally just run one thing and then run the other. And we'll, as long as the code in here is valid, and as long as we have a way to fix it up, or automating the fix-ups and other things are maybe not possible yet, but we're getting to the point where it's not very difficult because we have so much interoperability here that it's honestly, it's pretty cool. So, okay, the thing is, we need another address here because we're going to need this address. And this address actually it's relative to its proc. So I think if we want to fix this again, we're going to want to use procedure relative offsets. And that's something we need to work on as well. Procedure relative offset. Yep. Absolutely. So and actually, technically, we want to print out the vector each procedure. So really, while we're parsing these, we should parse them by procedure. Again, this is like one layer of generality after another layer of generality after another layer of generality. You just have to kind of start generalizing and see where you're going to get from that. Okay, so we're consistent. So now what we have to do is change all of our calculations. It's kind of annoying if you think about it, but at the same time, it's kind of necessary, and it's not really worth debugging this code any further without staging this correctly. We know that we can't do this. This can even be deleted. It's useless code. It'll never work. This will. And the idea is this will return after it does all the work. It'll be able to call back lambdas, but it'll return with a non-corrupted stack. Hopefully, maybe, doing some really crazy things in here. Yeah, I honestly I feel like we've gotten really far here to prove a bunch of stuff. And like we'll leave some of the comments. Maybe we can leave this, but this one's really dubious. This one is necessary because maybe if you do 32-bit code or a different system, you'll need to study the details of the machine language for the Lambda calls. If you need such an interoperability. There's also ways we could, generate the assembly for those as well. But the problem is that would make this algorithm O m plus n, and I was trying to leave this algorithm as O of it's already O of m plus n, but it would add another O of m, which would definitely, practically speaking, slow it down. O of 2m, right? It's again, you don't want to do extra O of m operations, especially. We're just trying to do extra O n operations at the worst. If you do something worse than that, there's just absolutely no point to any of this, because you're really going to suffer too much speed decrease. Whereas in a dense graph, not so bad. Let's see what else we've got to improve here. I know I'm trying to think what I'm forgetting. I know some of the calculations are still going to be wrong in there, but if we debug it, we should immediately be able to fix it now. And as I said, the next time we do this, we're going to just start generating copy-pastable code. We're going to, again, it's spending a lot of time on parsing, but you can see, look at the power now. We're starting to actually have some like traction on building a model. I'm not saying everything is perfect with the way I'm doing it, but it's every time I do more work, it's just getting better and better and better and better. There's no doubt about it. So, let's see. Next task was to fill this blueprint again. So the only way I see that we can do it is with another for each that's going to, yeah, I mean, we have to just start copying to it. Well, I mean, even a for loop would be just fine here. But we're going to have to mem copy this little tiny blueprint at the very start. So not jump topo. Jump topo comes after call blueprint. So call blueprints first. So where do we do all this stuff? So adjusting the blueprint, no problem. It's this P code block. Everywhere we do a computation, yeah, every calculation here is going to be wrong now by as many of these as we add. But what we can do is say the size, well, actually it's, what is it? The number of successors times the size of, what did I call it? Call blueprint. So this is going to be our magic value we add in everywhere, and we can just say, for now we do know the addresses already. Too many standard for eaches, right? This is just absolutely unnecessary. No, it's not. Not absolutely, but I mean, well, it's unnecessary, but we're going to need to already have executed some code to do this now. We can't fill in this part until we have the index map defined. What you do here. So this requires the index map. Well, actually, I mean, I guess the for each order would give us the indexes, but again, the correct thing to do, I think we took out the indexing everywhere else. Oh no, we didn't. We should take out that everywhere else. Ooh, that's annoying. I don't like it. Not when we spent O of n time to build an index map, we might as well always use it. Uh, Try to cut down on, again, actually keeping a track of a counter is faster than hash lookups, but, because even if they're O of 1, the actual hash calculation will require some instructions. Even if it's O of 1 instructions, it doesn't really matter. So, yeah, I'm going to take that off for a second, but I'm going to continue working here. There's no stopping until we drop here. We need to get this job done. My estimate now is still like at least an hour, because again, I'm just still solving some generality issues. The problem is I'm not trying to get this done as fast as I can. I'm trying to get this done so that it's reusable into the future as fast as I can. So that the future use makes it so it takes 3 or 4 times as long, and it makes it much more valuable, even if the instant reward is just getting it to work. Okay, so what we do is we do a mem copy, and we're going to do it into this p code block, which we've casted to a byte star. I'm going to add to it well, we add what the size of call blueprint times, what is it, index map sub x, where x is coming from this pair here that we're iterating over. And we're iterating too many times. We can combine a bunch of these, I think. I'm almost certain they all can be combined. I was a little worried about the lambdas being combined, though. In fact, why don't I just combine this? This is a mem copy. It's like a side effect, so I would just combine this. And the source will be call blueprint. And the size is going to just be the size of call blueprint. And we've got our mem copy. Okay, now we need to fix it too. Again, we could do this here as well. I'm almost wondering, should we just do it here instead of in the lambda generator? Kind of want to do what's the least confusing thing. I think it's better to just do both of them here. None of this matters, but we have to do the fix up, and we can make all the calculations here. Let's just capture that. And so, okay, this can just be p dot first. Now, everywhere we use I, we can just use p dot first, can't we? Oh, I equals, yeah, we're just going to delete this code. I don't like it because, as I said, it won't work. The stack has to be maintained in the assembly code. We can't let C go back to the main routine stack. Only if we're calling back into C and it comes back to us first. But once it enters that assembly, it can never come out. So there's no point in that code. There's no point in even having this I variable around at all. But there kind of is, actually. Let's just do it like that. So just one hash lookup. Now we're talking. That's much nicer. And so you can see what we've done here is to actually now load the blueprint in And we are going to need one more offset, which I think was that, I don't remember what I called it anymore. Jump topo offs. Oh yeah, we have this one too. Oh, do we not have that in the model as well? Okay, so we need to do this like procedure aligned as well. So it needs to know the procedure offset. Basically, it can save a base offset, but it needs to detect these proc statements. But it needs to detect them in the listing file. Ooh. Oh, that's perfect. Look at that. That's perfect. So we can see how this is formatted. Tab, tab, tab. Okay, so tab, 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 name proc. So that's what we need to look for. And then we'll just store the base of the procedure, and we can just subtract out and make everything work. And that will literally get copy and pastable code, because we can actually define like all of this. Well, we'll do it next round, not yet. Not yet. We're going to do one more round in here. We're going to do one more round in the generalizing, the parsing, and then we're going to do the final round and get this 100% working. To the point that it can solve stat equations faster than the virtual machine model, because it'll be using raw assembly language. And of course some C callbacks and stuff, which I have to tell you, those C callbacks look horribly inefficient. The way it's got so many different template classes in there, it just... But in the release build, as long as it works in the release build, then we're very happy, because it's so much faster. The release build will be like 1,000 times faster, and that's what we want. We want fast release builds. So this needs, all right, it didn't even get the offset. Okay. This doesn't change. We can just, again, wow, so many captures for this. So now we have to do an offset computation here. And then we need to cast this to a, well, I guess we're going to use, should we use size t here? Are we properly doing this everywhere? Yeah, size t or a void pointer. And in this case, actually, it's going to be a void pointer. So I mean, it'll be a void star star. Will it know that it's a void pointer? Well, actually, yeah, it'll know it's a pointer because it's a pointer to... First we do that computation. Guess we don't need the extra parentheses here. Do it like we do everywhere else. So this is going to be equal to the same address that the beginning of it is here. Same place we're putting the blueprint. Maybe we should define this as a base. Yeah, honestly, the code is so unwieldy right now that we're just going to say base BP, base of the blueprint. Should be a size t. The reason I'm doing this is because we're going to have to fix this calculation anyways. And it makes the code much more readable. Usually something you do after you write all the code, maybe. Okay, it won't work for this one though. Okay, so that one, now we can actually see where we're looking at the size of jump topo, which is probably only in 3 places. Yeah, here, here. All right, let's fix them all. So here we now know we need to add another thing, size of call blueprint plus this one times the successor size. So we need more memory. Here, we don't want size of jump topo. There's 2 problems here. The other problem is this one. Yeah, so jump topo offs. This actually needs to add more size of call blueprint. Actually, I had that like a useless line of code here representing this. Where did I do it? Size of call blueprint times what is its successor size? So that is what we need to add everywhere. Where did I put this? I put that useless line somewhere. Ah. One moment. Okay, sorry about this delay. Had to go to the restroom. I realized it was looking kind of dirty in there, so I did some cleaning. Okay, uh, just normal life stuff. Whatever. We're going back into this now. Okay, it's annoying me that I can't. Oh, here it is. Yeah, here's the useless line. Okay, I put it in the opposite order. Really, almost just prefer this order. So anywhere we see this, okay, this jump topo offs, yeah. Again, it doesn't need to use the size of this that here, but well, it needs it here. Yeah, we fix it before we copy it. It really didn't matter, but yeah, wait, yeah, except that's totally wrong. That's right. Okay, where else do we have size of jump topo? Here. Ooh. Yep, okay. This is the right order because this is the layout of the code. Okay, that probably needs a capture. Okay. Oh, a double capture. Kind of annoying because the value is already available. Yeah, well, actually, we could fix it by pre-computing it. There's ways we can. Oh, it doesn't like that. Oh, it's already captured. Huh. That's silly. Oh, it is using it. Oh wait, it's already captured here too. Why did I think it wasn't captured? Okay, so that's done. And finally, this one here. That's, again, why we put a variable there. Again, this one will be kind of long. And that's it. Okay, so what are the odds of this working? Not sure. But we're getting there now. We're getting even closer and closer. That's every iteration. I go back to assembly, I fix as much as I can. I go back to C, I fix as much as I can. And then when I go back to assembly the next time, I fix the parsing code in C, so we get closer and closer to a full model where we can actually use the assembler to generate C code, which is actually just byte arrays and constants, but let's call it blueprint code, so that we can do self-modifying blueprint codes without having to write binary byte code. It is pretty tricky what I'm doing here. Of course, the assembler doesn't write, it doesn't allow a syntax that allows us to do as much as we want. But we've worked around it, and it does enough that we don't even have to. We can always put DBs in there and stuff when we do need to write bytecode. Most of it we don't need to write. A small amount we could need to write. Oh, look at this. That is a massive jump chain. I don't even know what's going on anymore. I don't think we're going to figure out what's going on. I don't think I'm going to figure it out. So I think what I'm going to do is put the breakpoint at the entry. And we're going to just see if maybe I've not gotten things right here, but we're getting close. And the critical location is right here. Again, to me, this is so cool because to reuse this, I can generate lots of self-modifying code in the future, and it's going to be just so much faster the next time around. Everything learned from this lesson is helpful. So, okay. Okay, we see it moves racks to the first address. That looks perfect. Yeah, it's E something, E3C. We can see here the start of the function. Oh, this is working beautifully, isn't it? There's 4 nodes. Actually, this is a 4-node case, so it's okay. This is like the unsat case that has 1, 2, -1, -2, all these. And so we're going to call racks. Fine. It's going to pop it, too. So let's check out the stack pointer. The stack pointer is got an 8 here. We always want it to have an 8 in our code, except when we're going to call C code, where we want it to have a 0. We want it to be 16 byte aligned. So we get in here. So now we just kind of have to sit here walking through the code and just figuring out what's going to happen. Call racks. The first call racks we're hoping just works. It does. Notice we have an, we have an 8 here. Because we popped the return address. Oh, that could be an issue. The return address, we'd have an 8. Oh gosh. So there is some stack misalignment still going on here. Oh. I have to think about this. This is, again, I did pop and then I subtracted 8. So I think I've blown the stack already. Yeah. Simple as that. So when it calls this function, we're going to have to go and fix this anyways. As I said, we wanted this to be automatically generating everything. And then we're really happy because then we can start doing changes here very quickly. We don't have to mess around. We just copy and paste the new blueprint and we expect things to start working again. All right, so we've blown the stack because what we do here is we pop and we add. So we fix the alignment, we pop and we add. What? Totally wrong. The first thing I'm sure of right here is that we should add before we pop. This is definitely going to be causing crashes because obviously the return address comes after. We can't just pop. We need to add then pop. Oh, that's gonna mess things up. Oh man, the nice having the 08 byte there is gonna be. Oh, but the 48 is the same, isn't it? 48. Okay. I better fix that. Oh, that's cool. 48 will be the same first byte. Peak red lobe. +1. So we do peak red lobe +1. And now we've got this 48 8B. But now we'll just write these 4 bytes. We'll write 83 to 58, but we can actually just overwrite them. Again, we're still in the same code size, so it'll be 08 24 44 8B. 08 24 44 8. Yeah. Okay, so we do that, and that'll fix this to be doing the right order. So it'll change it to a peak. They share the same first byte now instead of the last one. Well, I mean, that's convenient that they, no matter what order we put them in, they'll share one byte. The first or the last byte, rather. So we can just do a single move instruction here. Cool. We can, oh, no. Yeah, peak right loc +1. Yeah, we do need to go kind of +1 for well-known reasons. This 48 is shared. And, oh, we have to regenerate this. So the one thing I didn't understand though was why the stack pointer would have been 8. Because I actually don't understand that because it should have been back aligned to 0 because when we make the call we're aligned to 0. It pushes to 8, but then the other routine returns and it goes back to 0. So we will take a look at that. That's actually an interesting question. But unfortunately, we have to go fix this because, as I said, it's not really nice to not finish the job here. And what we can do is we can just start by saying, well, we know what we're going to offset here, or we know what we're going to output here. But we have to be able to detect procedures. Now, how do we detect a procedure? Well, we have to detect it. There's no choice. So we're going to need another proc base. We'll just initialize it to 0. But we'll use this. And at some point, we need to detect the next procedure. We don't need to detect the end of one. We could. I mean, it's the same. It'll be effectively the same code. So what we've done is we output here a tab, but that's per line. We're also outputting extra commas. I don't think it matters. I don't think we need to solve that even. New lines. We'll move this whole printing loop somewhere else. This one here, so, and we'll clear the array. That's easy. We'll clear the vector rather, or we can move the vector somewhere else. Well, we could actually move the vector. We could move all these things in here. They don't need to be out there, but these are details that don't really concern us much. So where do I do it? Well, I have to do it. This is going to be like some kind of name. Again, we can change this from C out to just build an O stream, and eventually it's so easy to change the C out to just an O stream that will pick up everything at a later point for us. Just use spaces here. So the first thing we need to know is if it's a new procedure. And the way we can detect this, there's still going to be an offset to get out here. I'm guessing we can actually find not my favorite idea for this. So I guess we parse off what? What do we delete here? From the tab. So it's already going to have deleted it if we don't do it here. So we have to do something about that. So the problem here is we call it blueprint, call blueprint, and we're going to just change the names now. One way or another, we should be consistent. I think we call this jump topo. This we're going to call blueprint. So if it finds this proc tag, we're going to kind of have to do like a reverse tab search and all this type of stuff if we want to do this nicely. Or this is such a key thing here that we may want to just get the address right out of it. We can just actually make this an iStream. And we can grab the offset. And then we can have a name. And we can just grab the name. And then we can okay, but the problem is here we need to put the name, and we need to put this on the next one. And we need to kind of, remember to do this at the end. So there's just no good free way to do this quickly. If I want to do it quickly, I just copy the code again. Probably we should just fix this. So it'll put its offsets, and it'll clear the offset vector. Actually, it needs to do this first, and then it needs to do this. Okay, so there we go. So it's going to terminate the last one, then it's going to print this. So actually, we always know that we need to terminate something here. Kind of awkward, I know, but necessary nonetheless. And then we're going to open one, but we don't need to close one if this wasn't, like, for example, if this is -1 or something. So we could just say, and the name we can already consume here by putting it back out. We don't need to save it around. Fortunately, that will work. Okay, so we've done this. And this actually should go to proc base, right? In fact, we're doing this too quickly. Do this later. First, finish the old work, which we can do out here. We don't really care. We know it has to do it at the end. And let's see what happens here. Oh, not see what happens. A lot of code in here already. But still, it's still a wieldy file, 850 lines, and it's not going to get much longer. Most of this is just like figuring out the last details and get, oh wow, did that work? Oh, that's so cool. So, okay, you see this work paid off. You can see this is where you do some hard work, but it just pays off immediately. So already I can just copy and paste this in. The only thing I don't like about it, and I'll just fix it right on the fly, is that one tab doesn't look so good. We'll just put 4 spaces for the time being. I had this one. I think this will be sufficient. Okay. Wow. The order isn't the same anymore, and in a certain way, I don't care. I mean, again, actually, I like to see the blueprint with 0 because that's where the most code is, and if we want to check through offsets, it was useful. But as far as I can tell, we have now. Wow. Oh, it didn't work. Okay. It didn't work with these ones because it should have subtracted the base of the proc. And so we can actually figure out if it will work. It should be 0 always in these cases. And that's what we want to figure out if that does work. So, okay, we made one more mistake. And it's right here. It needs to subtract base proc. This should work. No. Proc base. Choose a name and stick with it. Which is exactly what I'm doing here. Yeah, it's working. So that is why I did all this work. I mean, again, it didn't take that long. You could see I somehow just pulled it off in a couple minutes, and now this generalizes all of this. The only thing is the order is wrong, but we can fix that by just regenerating the output the other way around. So the idea is now I can do this. I'm seeing the expected a semicolon. I'm wondering if I can't do that. It's a detail, but it would be one we should fix. Next round, not yet. No? Oh, this is really annoying. Okay. Let's fix, I don't know if we even need to fix that. I'm pretty sure you can have a trailing comma and there's no problem. But what you can't have is the braces in the brackets in the wrong place for declaring an array. So, oops, made a mistake. I need to fix this by hand. I almost won't even fix the comma necessarily right now, the trailing comma, because it doesn't, as I say, I don't think there's a C issue with any of that. And these are all relative now to their procedure. Okay. All right, that parse asm listing is getting quite powerful. It's making it now so I can really get work done quickly on this. Every time it's getting faster, as you can see. Sometimes you waste time, but again, you save it later. The more changes I'm gonna have to do, and I know this isn't trivial. So I make the call, the RSP goes to 8. Oh, goes to 8 here. That's why. So we've got this initial like misalignment going on. And what we should do here I don't want to toggle all the logic. I know this is absolutely annoying. Yeah, I mean, again, toggling all the logic would be like kind of one option. But again, if we call again immediately, we fix the stack. The stack's already in good shape. We pop, we break it again though. We just need to choose a model here. The problem is actually what I'm thinking about is like the jump sat. I'm thinking about some of these finishing touches. These are going to be very important. I need to get a drink or something. Wow, that is very tricky. All right. Yeah, I see this is a legitimate problem here. Because if I add to the stack pointer, which I really don't want to do, then I guess we just resynchronize on the other end. Because adding seems basically impossible, because by the time we get to the jump chain at the end, it has to be realigned to this having 8. Except in the case that we don't want it aligned to 8. Oh, it's just getting tricky. It is just getting tricky. But we can do this, we can generate code much better now, so if we need to fix it, it's not a big deal. So actually we are assuming, in the blueprint now, we're assuming that we've come from C, we're at 8, but we've come again into the blueprint from a call, so we're at 0 again. Does that mean we don't need to subtract 8? Well, if we're at 0, basically we want to stay consistently at 0. I almost feel we don't need to touch the stack at all anymore then. Well, somewhere we will need to, because when our calls are going to recurse to each other, this... Okay, we should stay zero aligned for the, because again, this is a kind of a little bit of a, not really recursive, but it's again calls, we're calling our own code, and we always need to stay aligned for the C code. The first thing I'm going to say is we don't need this. So I'm going to say, but call from C plus call to blueprint is realigned. So we don't need to do anything. We don't need anything about the shadow space. We don't care about that either. So we actually don't need any alignment here. We're aligned. And we don't care that it doesn't know how we aligned it with two calls. It doesn't matter. Again, it's only when we're going back into C that we care about this alignment. So when we pop here, however, we will cause like some issue on the stack. Right after, I mean, you can't get this right. Right after I've fixed this, now it looks like we will pop, but then we need to reserve 8 bytes. Or do we? Yeah, we do. So the only time we're actually going to pop is if it's not coming. Again, here it would just return up here. So here this changes to a return instruction. Oh, yeah, it's not going to change the pop into a return instruction. Yeah, we don't really care. We're just kind of letting this change to a ret instruction here. It'll cause fragmented code. We have to think if you don't want fragmented code, we'd have to like deal with 10-byte instruction here, which we don't want to deal with either. Maybe ret no op, but even then, this wouldn't be a valid assembly code. So, yeah, it's not worth dealing with it. It just doesn't matter. It does leave a fragment. Okay, so if we pop, then subtract, so we basically say the caller address, we don't need you, but we do need to align to 0, because if we call ourselves again, we do want to go back to 8. But no, we don't. Oh, wow. Are we heading back to the old code? My. So we're 0 aligned here, and we always want to start our own routine 0 line, which means we don't need any. No, we do need some buffering though, because yeah, we do need some buffering. Although I'm starting to think we can simplify this though. Really starting to think we're gonna just simplify all of this. No, it's never easy. It's never easy. Well, this actually, I mean, this is more complicated than it needs to be. All right, so we're saying we're always going to be even aligned here. That one we're going to have to guarantee. To always be even aligned here, but we also are going to have the return address at kind of a misaligned boundary. We're also going to say we're going to do that, and we just don't care. That's fine. So if it pops, as far as I can see, we don't need this. So now we have to go to the call location. If we're going to call C code, we definitely will need to reline, because now we're saying actually we're aligned for C in this case, but not for this case. No, we can't be inconsistent. So we will realign the stack, so we're realigned for C. So if we pop the return address, we'll just actually, we're adding to the stack and then subtracting again. No problem though. We're popping the value. We still need the value, but then we do need to actually not decrement the stack pointer. Maybe a move instruction would be better here. I actually am starting to think so, because we're not really popping the stack then. You're getting the value, but we don't want the stack pointer to change. Okay, so that actually is right. So now we're still aligned. We're ready to make calls. We're even aligned here. There's definitely inconsistency. This does not work. Because again, it depends where the call came from, but if the call came from here, why does this have to be so tricky? I'm guaranteeing here we're aligned to 0. Always. But when it makes this call and it returns, we don't know if we're still on the stack or not. So, this is a... I know this is like one of those like just tricky situations to get yourself out of here, because it has to be absolutely right. There's no way you're not going to get this to work if it's not precise. The only way I see of making this precise is to think about it though. So again, here we're at 8, so here we want to sub and add. Here we're jumping and pretending that the call was already, so it should be to 8, and that's fine. So here we're fine, here we're fine. Here we're saying we need to add 8 bytes. Is that true? I feel like we just need to modify a couple little things here and it'll work. But figuring out exactly what those are isn't necessarily easy. And because I have to think about the different contexts that on the stacks used, then I can get it right. All right. How's the stack used? Well, for one idea is that the stack is when the function calls itself, the stack is always now 0 aligned. It's already ready to call C functions. Which means there will be a pad and then the value. Yeah, effectively that's how we're looking at it. We're a pad and then the return value. We're looking at it almost the opposite way of the C convention, but we just don't care. So if that's the case, then actually we need to pop and then add, because we actually have the return value already, and then we need to add. So we'll have the 16 bytes. So now we need to only look at the re-entry case. So it'll be always the return address, and it'll always be on an even alignment. So we don't need to deal with this call. The only case here is this. The problem is if we put this move ESP8, which by the way always has to happen. So if we're going to subtract 8 from the stack pointer so that we end up back with a realignment, this function will do one of 3 things. It'll either return, which will leave us with a messed up stack. We could change it to add ESP8 in return, which would Wouldn't work because it has to. Yeah. Oh, this is just incredible. It'd have to like return to the address that's forward on the stack or something weird like that. That might work, but it's so weird. Um, yeah, there might be some way of doing that. Oh, it can return with extra 8 bytes popped off the stack. Yeah, it could do that. So that handles that case. Then there's the next cases. One where it was doing a peak and one where it's not doing a peak. So if it peaked and it wants to stay on the stack, then this value should also stay on the stack, and we take it off here. But if it was popping, I know it feels like we need to add here. We don't want to subtract. So if it popped the value, something it would do if it already had analyzed that node. Oh, no, no, no. No. Wait, this value only can come from there? Yeah, if this only comes from... Wait. Yeah, because if... Yeah, I guess if an... Yeah, no, it can never call them twice. So if it's either peaking or popping, and it's peaking it if the node is not on the stack or not already. Yeah. The question is if it's yeah, if the caller node's already on the stack. So if the caller, it could still pop here. Could still pop. Say, okay, I've popped off the return address. Which would actually align it back to 8. And it would need to then subtract 8 to realign it. Or it could actually add 8, but it can't because it doesn't really... Again, actually the easy thing to do there is... this is chaotic. Add RSP10. Oh, 10 hex. Yeah. So if it was... Oh, wait, is this... This is if it peaks. No. If it peaks at the stack, it shouldn't do anything. Ah. So if it pops the stack... Oh, this is complicated. It's annoyingly complicated because again, I almost feel like we need 3 cases here, which is what I'm trying to avoid, but I'm starting to like get backed into a corner where we've got the came from the original jump, came from the original calls. One question is then, why are we even calling them? Why not just jump to them? Why not just back out all the changes I've made and just call these? So I don't need to deal with this third case that we're adding here. If this came from the Yeah, the original call. Wait, we want to pop and subtract 8 bytes in that case. Want to pop here, subtract 8 bytes, and then we want to add the 8 bytes back later and just jump to the return address. That's fine. Actually, that's fine. It works. If it came from the other node, though, then we need to pop, subtract 8 bytes, but then we need to add 10 bytes. And if it peaks here, then we don't want to do anything. That gives me another perspective on this, and that's that this subtraction can be an add instruction on peak. We change this back to add 8. We don't worry about cleaning up after the call. Yeah, this is really clever. It's really tricky because we have to add like another fixing statement here. It's almost like we can just automatically just do the move because we know what node we're calling here. Because we've got it in racks. So if we take... Yeah, I have to say it probably works. Peak ret loc. If we change this from an add to a sub, I think we're good. Because basically we've, well, let's think about it. Maybe we're not, but we can, probably we can fix this one way or another by just changing even this byte or the instruction to add to sub. So if we come from the original one, we pop the return address, we sub 8 to align, and then later we're going to add 8. Okay, we've handled the original call. If we, again, maybe we could just use jumps there and do some other kind of logic, but that seems to be consistent. Otherwise, if we come from our own function for a pop, we pop, and then instead of reserving 8 bytes, we actually add. We actually get rid of the other 8 bytes that were saved. Done. And then actually we don't need to do anything. It's a no op. So pop and no op. There are going to be like 3 cases here. Because then the peak instruction, no op, no op. Well, peak and no op, no op. So we always want to make this a no op. Ah, yeah, that's weird. That's so weird. But I guess that you can just make it a no op and always. And then this one's kind of conditional on what's happening, if it's a peak or a pop. So if it's a pop, we're going to move like some byte pointer somewhere. I don't know, some value. And let's just build this so we can actually kind of sketch this out finally. So, okay, 4883 EC. C4 is add. Sub is EC. That answers all the questions. So, of course, there might be a way to actually subtract using a negative, but we don't want to do that. We want to do this straightforward. So all we have to do though is change this byte. So if we do peak ret loc, I mean, we can always add more labels, or we can just say peak ret loc +1 +1 +1. Okay, yeah, so we've gone 3 bytes in, 0, 1, 2, 3. And we want to just change that to a C4. So the default, when it gets its initial call, is to reserve memory. But if it's a pop from one of its own nodes, the default is actually to take away the memory, and we'll just know about. I think this works. Admittedly complicated. So instead of subtract, we'll just change it to an add. And we kind of explained that we change it to an add, yet we'll also change it again to this instruction, which won't work anymore because we've screwed up the order here, right? We pop the racks first. So we've got this 58 to 08 scenario again, whereas the instruction we want to put there ends with a 08. So we do the same thing we were doing before, and we change it back to the reverse endian of 24, 44, 8b, 48. Wow. And I think we're good to go. Yeah, I don't want to run into any more issues with this. I want the stack perfectly aligned from now on. And as I say, I think I've got the idea here. And I want to see where it's going to get now. So let's run this again and regenerate the code. Maybe regenerate the code. Okay, the only thing is those commas, which I said shouldn't matter at all. And if we really think they do, we'll fix that. Not too hard to fix. Okay, that's cool that we can just do this now. All right, let's hope we don't have to change the assembly anymore, but now changing it is much faster. Now, mostly it's just going to be conceptual issues from now on. So we get in here, we're at 8 on the stack, and then, of course, we go to 0. Now, we're going to come down here. We're going to pop an address, the return address, which is where the next jump instructional, or the next call instruction will be. And then we're going to subtract from the ESP. So we're going to save 8 bytes on the ESP again, no problem there. We do some self-modifying stuff. We move racks 2, good, there's 2 successors. Compare racks with 0, Okay, now this call we can skip because it just gets the address of a node. And in racks, we see the address of a node. Oh, why? That offset looks bad. And the code looks totally corrupted here, doesn't it? BD. BD. Okay. This is easy. We can just look at the ASM here. I think I know what happened. Where do we do this call? Where's the call loc? It's right before call loc. Okay, so... oh. easy thing to do is to look in here and see what it's generated as the relative offset that I tried to do. Yeah. Okay, that one looks good. Wait a second. Here it is. A8. C680 FFFFA C4. All right, let's do it again. This looks absolutely corrupted. Oh, yeah, it is. Okay, it is corrupted. Wait. It shouldn't be, though. Something corrupted some of the memory here. I see BD, which looks good. Wait a second, BD. The third move here. Yeah, this is tricky right now. I have to kind of like study some details with this. Um, BD was what? Top up stack loc? Oh, yeah, that's right. This is. Oh. Oh. Can't get away with that. Uh-huh. Yeah, it's okay. I was corrupting the. Yeah. Okay, that explains it. Obviously, top up stack loc needs to be kept in the right place. All right. Yeah, because this is setting up for this call down here. Okay. Well, I like when solutions come here, but again, it is so worth it that I built this stuff because you can see I'm generating assembly again and again. It's just making mistakes. Annoying as it is, it's hard to not make any mistakes when you're doing this kind of code. Okay, gonna highlight all that and replace it. Again, maybe we should automate this too. But for the moment, I'm willing to do this much work. Mainly because I'm hoping I'm close now. I'm hoping this is starting to get more and more debuggable, where call recursion at least works, and we're starting to get to a point where we can be reasonably happy with this. So let's make sure we're getting through to that point now. Can just step through quickly, see that we're passing, see that this is working. Okay, Rax minus 58. What's Rax and what's Rax minus 58? Rax is 205. Oh yeah, I won't actually know that this worked yet. Well, we'll know when we make the call, and we're going to move 90s. Okay, well, we'll see if these were computed correctly or not. Oh, they might not be. We can just go into memory and take a look. So where is my memory view? One AD. Let's look at it. No, this is not right. It's all corrupted, actually. It's totally corrupted. So the first thing we have to fix is this. Can I explain why? I can't, because we haven't touched that memory yet. This is so strange. Now you can see here, subtract, move, 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 compare. No, yeah. I think this has been updated with the C3, but yeah, it doesn't really matter. So far, I like what I see here is the basic gist of everything. I'm looking for the next prototype. Oh, it's down here. Ah, actually, it's further down than I think it is. No? Yes or no? It's down here. It's down here. So it's, oh yeah, it's at 205. That's what we wanted, 205. So how did it get one? Oh, it's subtracted? Oh. Oh, it's subtracted? Oh, we know this is going to crash. This has to be absolutely precise. What we want is this instruction here. And we might as well just calculate it now so that we don't have to ever deal with this again. We want this byte, 205, and what is this, 233? So 233 hex minus 205 is 2e. So we wanted 2e in there, plus 2e. Instead, we're seeing something wrong here. We are seeing minus 58. Okay, let's get minus 58 over to 2e somehow. I wonder how many of these types of mistakes are around. Is this, it should use RIP relative addressing. Yeah, actually, well, it doesn't matter, actually. These are relative offsets anyways. So we're saying peak, peak ret loc. Oh, wait a second. This will be negative. We want to do this the opposite direction, I guess. But we still need to use $, and then it'll be $ plus something. Yeah, oh wow. Peak ret loc. +1, +1, +1. That looks good. Parentheses around this one. Okay, so we need to know how many bytes that was. Yeah, I forgot. There's all these little mechanical things. We have to check all of this. This is actually 6 bytes, right? So 1, 2. Oh no, it's 7 bytes. Oh, so it's right. 4A. Actually, we can easily tell if these are right or wrong. It's wrong. 4A is like here. Oh wait, rip relative. We were saying rip relative. But no, actually this is not rip relative. Oh, it's saying this is relocated. Oh, wait a second. Actually, oh. This one actually is supposed to be the pointer subtraction. Yeah, I'm just making some mistakes here. Okay, this actually was supposed to be much simpler than... Okay, this is so tricky because you really have to think every time you're doing this stuff, like uh, which type of operation. So let's see if that works. It shouldn't be a relative. It shouldn't be a rip relative at all. This one, yes. This one's if it's relative to the current node, then we use it. Otherwise, we don't use it. If it's another node, we're not using it because we already have the other node base and we can just add or subtract to it. And if I look here, uh-oh, where is it? I don't see it now. Here, okay, 4A. My peak ret low. Yeah, because why are we even subtracting? Yeah, I know why we're subtracting. Again, it's kind of arbitrary. What we really want to actually say is peak rect loc minus node adder loc. Yeah, I'm really screwing all this up. Plus 3 minus node adder loc. And that should be the end of this. It's not relative to this instruction. This is absolute addressing here. And actually, we know that it's going to be the same situation here, where we're actually... Actually, it makes the code easier. You don't have to use the displacement and the current instruction size and all this. In this case, actually, we do want... Oh, wait a second. Yeah, look. Yeah. Rax plus that. It's an absolute address from the base of the function. Same here. That should solve a bunch of problems. Okay, that should definitely solve some problems. Now, finish this. Now we're going to get somewhere. Okay, I think I'm going to move on to like being able to recurse nodes, which is the first great sign of this diabolically hard task. Again, my goal today is just to finish this task now, because you can see how diabolically tricky it is, so just getting it working would be amazing. And so, okay, I'm going to take a camera break. But I'm pretty sure it can be done. This is starting to feel really close. Although, again, I don't know how many of these types of issues I'm going to run into, but again, we're now down to true debugging of this, and it should be all good. So let's see if this actually works now. Do we see locations that we wanted to see in here? I think the answer is yes. Okay, we see 2E. Yeah, it's perfect. Okay, it's obviously... I need to be careful with these precise computations, though. I know I'm almost thinking of integrating the generation into the build process, but that'll take some time too, so yeah. But doing it is really instructive as well, because then you can automate your whole build and you don't need to like keep copying and pasting code that you're generating, which is pretty annoying, to be honest. I would rather have this all automated. Again, totally becomes reusable. But then you have to think about how do you automate things on Windows and Linux. Maybe you have to use CMake or something to make it really nice. And so you have to ask all those questions. Probably Visual Studio is not something I want to depend on. I'm just using it as a tool, but that's it. Okay, please tell me we can kind of start recursing functions and start gaining some traction here. All right. So we've got that. Okay, so now, uh-oh. I mean, does this look wrong? This looks like wrong. Instead of C4, it put a 0? I mean, I'm looking at the list file, and this just looks blatantly wrong. What on earth? Is this a bug in Amasm? That is so weird. 0C4 is a perfectly fine byte. You gotta be joking. Now that's annoying. Okay, 14F. I assume that's right. I assume it's going to call the next function. Okay, so what is our stack pointer? These are the things we have to kind of trace and make sure we're doing this right. So it's 8, so it's going to go back to 0. Oh. Oh, I used F10. So it's got the right pointer here, but it's refusing to call it correctly. FFDO. Let's see if that's... Yeah, I may have to investigate why the ASM is not generating a C4 byte here. And just looks wrong. Always putting a 0 there. Yeah, I mean, we can just use DB as a workaround for the meantime, but that is pretty annoying. I know it'll crash if we don't fix that. So the temporary workaround will be just to use a DB, because I don't know what else to do. I can't even begin to explain what is going on here. Obviously, it looks like a bug in MASM, and I hope we're not going to keep hitting these. Oh, does it? It's going to do the same with the C3 or not? I don't think so. That one works. So why on earth can it do this one correctly? Oh, the difference is this is relative. Yeah, probably a bug in the compiler. Now, the thing is, we don't want to use RIP relative addressing. This is... Hmm. Maybe we just need to put... I'm looking at that RIP relative website to decide what the key for this is. Because if we use a variable, it's supposed to use RIP relative. What if we used call racks with brackets? Oh wait, but this one's working? It's this one that's not working. All right, let's take a look again. We'll use F11. All right, here's the bad 0. Maybe something's going on with that. Okay, so this call racks worked. It wasn't RIP relative there. Maybe something just, it wasn't showing me what's going on. Okay, it's the stack pointer. Oh. So we messed up our stack pointer? Hmm. Okay. Okay. So I'm going in the wrong direction here. There was nothing wrong with the addressing. The problem is the stack pointer. So let's watch where the stack pointer gets corrupt. Maybe the lambda. So maybe we're not... Oh, I thought we had solved that already. Okay, so if we're messing up with the lambda... Okay, I see the RSP is CF218, whatever. So far, so good. So it's obviously going to be good for this call. So let's call, and we see CF218 at 40. No, it's still good. Oh, because I subtract from the ESP. Oh gosh, don't tell me I have these types of bugs. I do. Have to be careful. Okay, so we need to regenerate the blueprint. This time we have the fix for the the bad ML output, probably this should be reported as a bug to Microsoft. Again, when you're doing really tricky stuff like this, it turns out nobody's ever used it and it's never been tested. So you can't say it's going to be that surprising that you're going to end up finding assembler bugs, especially since ML is not particularly great these days, but it does still handle a lot of code. So I mean, can't say too much about it, but yeah, this is tedious. Yeah, this is like a prediction chance. How long is it going to take me to get this diabolical stuff working? Okay, so now we're not corrupting the stack pointer. Yeah, I should have realized that was the stack, because you're not writing to something that you're calling. So, okay, here we go. Now we use F11, and we make sure that we can get into this function. Okay, we got into the function. Okay, now we want to check a couple things are right here. But basically, this looks good. Looks good. Oh, already we got corrupt. After incorrects. Move. And then what I see is 0000002408. So after this move instruction, where it's supposed to be this pop, this sequence right here. Oh, did it also, it blew that as well? Well, we can look at the listing and see why it would have blown that. Yeah, but a lot of this looks like assembly issues. So we did try to write a C4, and we also tried to write this. Oh, look at this. What is going on here? Oh man, it's really messing up. Oh, but I can see it wrote it actually correctly to the right place, but it actually wrote the wrong value. Because we want it to peak, and it was going to peak, but this is ridiculous. Oh, this is so annoying. So it can't do relative address. Two bugs. We've found two bugs. Oh man. The good news is it'll generate the right opcode except for the immediate value. I can't even begin to explain why this is happening. Does the 9090 work? It's so weird. I see. So the problem turns out to be the 40 form. Or who knows? Yeah, it looks like it though. And then it puts a 2B in there for the offset. So when it's using the byte SIB variation, oh man, this is so annoying. Really, the compiler can't deal with this. This is just uh yeah, like it wants a byte here, so it only takes a byte here, or who knows, what on earth they were thinking when they did this. It's terrible. The 9090 one works because the address that it's the displacement that it's adding to racks is big enough, I guess, that it figures out how to handle that. Wow. It's crazy. This is legitimately a bug. I mean, so weird. Yeah, I didn't think I was going to have to be debugging these types of issues. I thought if I wrote valid assembly, I was going to get valid assembly. Okay, nothing to do with this comment or something else. I'm trying to decide, is there some other reason this is happening? Put the comment on the next line. No. There is absolutely no explanation for why it's zeroing out all these other bytes. Oh man, this is absolutely annoying. So we just put some DB fixes in here for the time being. And now we can actually write it in the normal order. 48, 8B, 40, 24, right? 48, 8B, 44, 24, yeah. So now we can do it that way. And we've got our 7-byte instruction. Whew. Well, actually, the thing is, it is starting to work, though. So, I mean, as much as this is super annoying assembler bugs, okay, I mean, this is a joke. This Microsoft's assembler is not behaving very nicely here. This should be reported, actually, as a bug. This is like... again, I'll report it later. I think I want to just get this working as fast as humanly possible. And I'm going to just have to work around any bugs. Probably the only Rax relative addressing we do there, but there might be a few more. So it might not be... But we can actually look at the dump. We can look at the listing file and easily see. Now, I don't know if it's a listing file only mistake or what, but it's obviously a bug. I'm sure they would accept it if you can reproduce this. They will accept that bug, and they might fix it some year. So I'm not like rushing to go report it because I know that I'm going to have to solve it with ML without. Again, that blueprint will be portable anyways. It'll work on Linux. You could generate it in Windows, and you don't necessarily need to make things portable for Linux using the generation process. You could generate the code in one environment only. Whether you want to do it for the generation process or not is kind of a question. Okay, trying again. I'm expecting lots of problems right now with this type of stuff, unfortunately. So we get into the next node. Okay, now it's right. Now it racks the RSP plus 8. Let's see if this works. Oh. That'll be wrong. It should just move the RSP. BB. BB. Is BB right? It'd be the wrong one, right? No, it's right. What? That's right? Oh yeah, because we're taking... Actually, no, that's right. That's absolutely right. Okay. Keep going. We're expecting it to, have 2 to go through. This one's like a big, strongly connected component. So we're expecting to go all the way into the inner one. And we're kind of expecting this code all works now. Yeah, this is great. We're actually getting to the third node, move rack 0. Okay, it called one of its previous nodes, and it's going to return. It's going to mess up the stack. It can't return. And we can fix that. I see that it can't just return because it will corrupt the stack. It needs to also return 8. So we probably can just fix this really easily. As I'm saying, we want the stack to be restored. Right now the stack pointer's even, but it's going to go back to 8, which is not what we want. We pushed, we called, it was back in even alignment, and now we're, okay. Yeah. Anyways, I said this before, and I just forgot to put it here. So we can see this needs to be ret 8. Fortunately, there is an instruction in assembly which lets us do this. So we can just kind of like look at what it would be. If even this works in ML, I think it will. C2 008, okay. We'll just put the bytes here so we know what they are. So it's actually C20800, but whatever. So if we want that to be 08 or 0008 C2, something like that. 90. Wait, the last byte needs to be C2, and after that should be a 08, and then it should be a 00, and then we don't really care after that point. And probably it's going to not generate correct assembly code. Oh no, it maybe, because this one's not using Rax relative, it works. Okay, so that's great. Oh, yeah, that's great. So it will return, yeah, okay. So again, this is all the type of stuff that we have to solve. Then the last part's going to be solving the jump chain. There's not much left to do if you think about it. Once you get this part this much working, you've seen it all before. There's going to be no new concepts coming up here. It's mostly now just debugging the natural logic and finding all these weird issues with the assembler and with the written assembly code where actually we've got bugs in it. So we're going now for that 1 hour actually solve it. I think now we can safely say we're within an hour because we've got the whole first part of it actually working. The self-modifying stuff, it's all come together, and we know, okay, that. We've already solved a huge number of issues with the details. So there's no more unknown details to look up. It's all like just grinding your way through it at this point, using all the knowledge you already have. That is good news. So we're going to go to through this call, and then we go to the second Rax call, and now we step in. We see that this is still working. We get to the next Rax call. It's going to get a successor we've already visited. That's fine. And if it knew they were in a component, actually it could short circuit even earlier, possibly. Is there a way for them to know that they have to be in the same component? Yes, actually it could, but it doesn't know all the nodes in the component. So it'd be silly to try to guess if it's, seen the sibling as well. Yeah, actually it's a good question. How much can you short circuit finding the sibling? Again, but checking if it's on the stack is not really a good option either. It's better to wait till the component's finished. Okay, this is the final call here, right? Whoa. Move RCX. Oh, this is wrong. I see the C20800, but this isn't what we wanted. How did that happen? Oh, wait, do we not node add or loc? We must have not calculated something. Oh, because we used $-7 isn't going to work anymore because we've changed the instruction size. So actually, 1, 2, 4, 10, $-10, which is, it would explain it. Okay, I'm gonna actually start spelling out what's going on here, because we can kind of remember that this is a 4-bit displacement with a 4-bit or 4-byte immediate value, and we can have it generate the right code for us. So this instruction here should have been FFFFBB. In fact, maybe we can just fix it by hand. It's just a bad calculation. And this is hard. This is hard. I think it's this one. So we're looking for C705. Somewhere there's a C705. Yeah, FFFFBE. Now it's BB. Okay. And how many times just to get through, and we haven't even started returning, and we want to get to that. We want to see the low link. We want to, and then finally it'll get to the root one where we just have to deal with one component and make sure the jump chain gets built and all the stack gets popped off. Honestly, this is kind of fun right now. This isn't bad. Kind of. Because my expectation is that each time we keep making it further and further, the less chance of making an error again, right? Because we know the concepts, and we're already testing so many concepts right here of how this self-modifying code has to work. So it goes to the first node, -1 to -2, who knows what it's doing. In reality, I don't care as much as looking at the assembly. There we are, return 8. That's better. That's much better. So we're back at CFO. Okay, so 64EB. This one is interesting. So it's found a new low link. That's good, actually. It found a new low link at 0. That doesn't look right. Oh no, it is. It's right. It is right. Actually, that's absolutely right. It's the first component. Yeah, so okay. So it's going to change this one to 64EB, and we just need to make sure that's right. Okay. Move racks 1. That's good. It's not 2 anymore. It's 1. Compare with 0. It's not. So now we're going to get the next node. Pointer to a node. This one should be a new one because not itself. We don't have self calls. There's no self loops in an implication graph. So let's see where this one's going to call. Okay. Again, this one's going to have the same. It's going to now call 2 more. And we really don't care again. Okay. They should probably both already have been visited. Yeah, okay, this one was already visited. We move 1, we return, the AX is 1. We're going to check. We're going to also say, okay, 1 is less than whatever this one was, 3. Oh, it's perfect. Okay. I like seeing it work. So this is huge. This is half of the code almost. Let's say a third though, because we're getting about a third code coverage here, where we're going to say probably this will reliably work. Wow, tricky stuff. Let's see if it's calling a new node or one it already called. Okay, it's a new node. This is the last node that it's going to visit. So it's never going to visit another node. And this node will always call return. And this node actually has to make it through alive. And actually that's beautiful because then we're going to start seeing if it's going to return properly. If this stuff works, I'll tell you, it's amazing. We've made it like, I would say halfway at this point. Yes, we don't deal with the components. Yes, we don't deal with the exiting. So maybe like 40% realistically of code coverage. And conceptually, it's nearly 100. Yes, returning at the end might be tricky, but shouldn't be. I mean, it's just stack pointer adjustments. Most of this you can just eyeball out at this point. There's nothing particularly tricky going on. I'm just going to run right through the calls because I know it's going to return. And yeah, I hope it changed that to an EV because obviously... Okay, so now it should exit this loop. Wow, it's making it through. Compare AX with 2. What? It should jump. I think this is just stale. Yeah, it is. Okay. Okay. Oh, ouch. Oh, no, no, no. This is all stale. This is all stale because it doesn't know about self-modifying code. Yeah, okay, so it's going to compare RSP. CDO with CDO. And it won't be on the stack. And what's it pushing on the stack? A wrong value. Great. I mean, it's not great, but it's at least great that we know now. It's pushing the relative address, which we don't want. We want it to push the address, the absolute address of its node. I, according to this, we can use load effective address of the RIP, and we could add it on there. And then we can just make sure that it's the address after this call instruction, and we're done. So FFDO is like the relative address to this push to where this call is, but we know this is blundering, so. Now pushing also means it needs to subtract. It needs to keep so it's going to do a fair balance here. So this will happen. Oh, I see. It wants to push not an immediate value, but it wants to. So again, this isn't going to work anyway, so we can just fix that right off the bat. Whew. I'm telling you, this is really exciting because we've now gotten this amount of the code done, which contains a lot of most of the conceptual trickiness and a lot of the trickiness. Yes, I admit that this loop right here is going to be tricky, and I admit that this final jump activity, actually this stuff is pretty easy if it works in one case. Again, it's simple. It's not doing any self-modifying code. So actually, I would say that that's why I'm saying like we're maybe 50% done because the only other tricky part is this self-modifying code. This stuff, it's just a chain of jumps. There's not a whole lot going on to it. Yes, it's calling a lambda, but we fix the stack. We deal with this stuff in a way that's perfect. We've already tested that we know how to do that. And yes, jumping back to the return address seems like it's going to be a problem. But again, honestly, logically, we know there's no problem with that. So as long as the stack's been maintained, if the stack is not empty now, we will crash. Unlike in the simulation where a non-empty stack isn't like a huge problem, here it definitely is. So the thing I kind of want to do here, and I have no idea if this is going to work, but I kind of want to like load the effective address. I don't think we need racks here, so we'll just use that. And I want to use rip plus. Ooh. Now this subtract from the stack won't work because we subtract and then we call. Oh, that's a big problem, isn't it? Oh no. Oh no, no, no. The call, yeah, here it always should be at the top of the stack. So we pop and then subtract. So actually, yeah, since it should be at the top of the stack, we should subtract before we push. Okay, another bug we fix. Getting all the bugs out of the way. It's awesome. Awesome because we're going to be just to this one loop, and then the jump code should just be automatic if we get this loop right, and it doesn't blunder the stack. So okay. Oh. Okay, yeah, here it pops the racks first, and then okay, this is perfect. And then as long as these computations are all correct, which I think they are, it's just awesome. It will just work. We will just get a chain of jumps. Then it'll call and return, call, return. Everything is just work perfectly. Oh shoot! Again, I find another situation where we're gonna blunder. The problem is if we return near with 8 bytes, it can only have been called from. Oh gosh, this is just a there is a little bit of a nightmare with these stupid 8-byte pads. I almost think we should just take them all out and not care if C is picky about that. It probably isn't that picky, even at least in a debug build. You can add them back in later. Oh, because they're killing me. I mean, obviously it's going to cause more problems. So far the ordering is right, but now this return near is going to be a problem because it can't return near with 8 bytes if it doesn't have 8 bytes extra, and it won't in the call blueprint. The call blueprint, of course, isn't giving an extra 8 bytes. Should it always give an extra 8 bytes? That might just be the solution. Actually, it might just be the solution that we just always subtract and add the bytes, and then just add the bytes back afterwards. But we can't add them back afterwards. I don't know what to do about that. That is really, yeah. That's these types of little things, but they're design issues too, and they're like logical issues. And I will blow the stack, and it will never work. Again, I can walk through it in the debugger, and it may work all the way to the end. It still doesn't mean that it works. Let's see if that works. I don't understand. Undefined symbol rip. I know the problem is using labels. The problem is we have to relocate this stuff. We could just add the node location. If we want, that's one way of doing it. We can just generate the code with another offset and add, but it just seems ridiculous that we can't get this to work the way we want it to. We can do a workaround for now by just calling to get it off the stack and popping. It's a horrible, ugly hack. Uh, in fact, I don't even know if this would work if we had the rip value. I have to think about this because actually, what is it going to generate for assembly code? If it would generate a rip relative. Oh, yeah, we know how to do that, don't we? Wait a second. Just force it to use rip relative addressing. Wait a second. Can't we just push it directly then? Yeah. Oh, can't. Doesn't like that. Oh, so actually don't even try it. No, that one's going to require a something cinnamon like this. Uh-oh. Yeah, we have to use indirect addressing. The problem with this is it won't work. Well, what it will do is it won't push the address though. It'll push what's at that address, which will be some code here. It'll push this compare, push 8 bytes of that compare instruction. We don't want that. What we want to do is get the address and just push the address. So what we want is this. The only way to do it is using load effective address. But you have to say that it's a keyword pointer, even though it doesn't matter because it's loading the address. I mean, it's just a thing, whatever. Actually, does it matter? The addressing mode on this, as far as I can tell, it wouldn't matter. Now it's going to be annoying to walk through the code because this is really deep into the code. Could just let it run and see if we get lucky and we can understand where it crashes, or... So what I see is somewhere there's a push. What I need to see is that somewhere there's a push. Here it is, here. It should be fine because this is now the 05 mode. It should be the rip relative. And if it's rip relative, we're good. It should load the effective address. Now we see 488D05. Because again, we don't know this is a quad word. I would actually prefer this. Yeah, it doesn't make any difference at all. So that's what I said. It doesn't matter. But I would prefer to leave that as the final code. So, of course, the push racks should be there. It doesn't matter where you put the LEA. Okay, so this is, again, yet another generation here. And it's annoying because this is 4 nodes in now, but I mean, we could try to fake it, but this is about as simple of a unsatisfied equation as I can come up with. Unfortunately, there's just no choice. We're going to hope that it crashes out in a better way than it's done before. So we can just look at where it's going to crash and just start trying to figure it out. Again, walking through it line by line, though, is extremely useful time spent because it'll find all sorts of other hidden bugs that you might otherwise just miss. And that's something we don't want to do. We don't want to miss, like... Because, again, eventually we're going to need the stack to be correct. And right now I don't even have a strategy for that, as we know. It's like a problem. Okay. Uh-oh. So it's hard to know what happened here, but it seems like it must have gotten 0 in my phone. All right. I see somebody else commenting. Sorry if I've not been very responsive. It's cool to see somebody in the chat. Um, but yeah, I am doing C++, so, but also assembly language. So we'll see, and we'll see how long I can go. If I can't get it done in 3 hours, it's a bad situation for today. For getting it done. Of course I want it done. I don't want to deal with this again. I want it finished ASAP. No excuse to not have it done today. However, right now I don't know why it's crashing, so the only thing to do is to start the long walk here. So we're doing a long walk through this assembly language, and unfortunately I have to keep mixing F10 and now F11. Okay, so it's returning a valid pointer. Goes into the next node. F10, F11, into the next node. This one's going to its next node, F11, shift F11, 10, F11, into the next node. I just want to see it kind of, this will be the last interesting thing going on, then we can just use F10, because we know it should be returning everywhere. Okay. Next one. And there we are. And F11, the last node. And now we can just F10 and hope we can figure out what's going on. Okay, so far so good. Okay, so now it's going to deal with this stack issue. So I see it's loading 47E, and what do we think of 47E? Well, we think it's off by a few bytes here. That's what we think about it. Definitely not happy about 47E here. It should be 47A. So this is 14 minus 10, so 4 bytes off. And then the question to ask here is why 4 bytes off? Because this load effective address instruction is 7 bytes, that would make sense. The simplest explanation is the load effective address instruction. Load effective address is 7 bytes. Yep, okay. No surprise there. Alright, let's just, yeah. Okay, so it's pushing the wrong address, but it's still, let's see if we can, that's not going to be an immediate problem. That'll be a problem later on. Let's see what's happening after that. See if we can catch 2 bugs right now. We don't want to, uh-oh. Push racks, not push pop racks. It's going to jump here. It's just stale code here. Now it's going to move racks. It says 0. The low link, and the low link is 0. We've got 4 nops. 4 nops, good, because we've got our stack with valid stuff on it. And the CX619 should be the calling node, which it is. Wow. Now, what did we assume here? Oh, wait a second. Well, now I know what's going on. Obviously, racks here is bad. And the question is, how on earth did it get this on the stack? This should have been popped off the stack. Stack alignment issues. It probably was on the stack, but we're playing a lot with the stack, and we've just simply managed to not so fast, because It would have been saved through this. Yeah, actually, I mean, it's, yeah, through here. RSP, let's find Rax. Rax is RSP plus 8. We're getting close, but this something's wrong here. Popping the racks is definitely the right decision because the subtract has to come after. We know that this is a direct call. The return address is going to be right then and there. There's no problem with that. I mean, I didn't even want to fix the push instruction thing. I can regenerate or just change one byte to fix it, but that's not the issue right now. That will come later when it is dealing with the stack. But this actually came, a wrong pointer came through. I mean, obviously, it should have been returning to the right call hook. Doesn't make any sense. Yeah, this is very, very strange. I believe it was doing a peak. Oh, then this must be wrong. Okay, a call instruction pushes onto the stack. Pushing onto the stack moves the data and then adds to the stack pointer. Wait. Okay, I need a pseudocode for the push instruction. So I go to Felix Cloudier's website where he has this. And then, so RSP minus 8, it subtracts, and then it moves. Oh. So this is wrong. Okay, that explains it. Okay, perfect. Finally, something makes sense here. So we actually want to move Rax RSP. Not. Now let's just check what that instruction works out to be. Oh, it's... Now the 08 is no longer an issue. Well, it doesn't matter. It's not going to align correctly. We can't pop. Oh, actually it does matter, because if we can't pop, we better nop. Can't pop, you nop. 48 8B EC08, does it align with any of that? Yeah, it does. EC08. 48 8B. So we could actually just, but we need 2 move instructions now. Okay. Well, let's save the code. We're taking out the 08. Again, I kind of don't care how we end up doing this. I feel like the old idea with using the offset plus 8 is going to be wrong. So we definitely need to do something here on these lines. So if we go to the peak log, we can actually just say to move a 90. So we'll change that to a nop if it works, which it probably won't. Oh, that is stunningly annoying. What about a word pointer here? So at this point, we want to add, we want to skip the no op, and we want to skip these. No, we can't skip all these, can we? 488B 0424. No. We actually end up just adding an instruction here, and this one has to be +1. Yeah, I am kind of annoyed at the assembler for having these issues. I don't know if we're going to run into the same issues later. (742C). All right. So that should be the correct fix-up now. And we should get a different error. We should be hopefully above and beyond this stuff. We are starting to return, all sorts of good stuff starting to happen now. Again, now the next place we're trying to get to is the component. We're really, really pushing that right now. And as I point out, that's like our halfway point if we can actually get to components and all this call business is working. And the hope is that it's actually more than halfway because, again, the experience gained should be able to add up to faster code. And so we see where we're going to get here. Hope it works. Oh wait, we need to turn off the... Yeah, I should just integrate this somehow or another. CMake is the best choice. But again, it's like a totally separate project to deal with the build process. Okay. Oh, this looks ugly. It made it into the component code. That's amazing. It made it into the component code, and it's okay. This is awesome. This is just pure awesomeness right here. I'm getting so tired. This is like, honestly, this has just been a real serious work bout right here. I'm thinking of going and getting some coffee right now and taking a break from stream because this is just, it's going so well right now. Again, this is going to probably be my last day before I even maybe write a paper about this whole thing. This is just, it's just so cool to be able to actually get this accomplished. So we'll see how things continue to go here. I have some videos on YouTube now. Back with these like two statements here, and we just finished the job off like we do before. Because again, the problem is there's one that's being used as a pointer to the tail. It's really a tail pointer, and again, it's kind of tricky the way I do it. And again, I'm looking at this video, and it's like so unreadable. Like, huh. 360p. Start topos actually point, then to fill doesn't need to be. Wow. You can just use it directly, and that's so weird because the video I uploaded the day before had really good quality. It's so blurry that not even worth talking about. It's not, you can't read anything, even if you have a laptop monitor or something. Yeah, something went wrong. There's a lot of interesting. I don't know how to get them into actual assembly instructions. Well, I'll figure it out later. Whatever. Just wanted to check. I think on Twitch it's fine. Yeah, that's interesting. I don't know. Maybe you have to download it and upload it. Yeah, that's interesting. Well, I don't know. I don't know why it uploads one in high quality. This one's 30 minutes longer. I worked 8.5 hours straight. That's how you do this stuff, though. You have to get serious about it. And right now, I am serious, and I'm almost done. As I said, we've gotten the halfway point now where I think it's hitting components, but I'm not sure. To be honest, I'm not sure. Well, actually, this stack is not traceable because the debugger won't work with the stack here because we've not used the proper. We've used a double call. It won't work with a call back to back with a call. That's right. It just won't. And right now we don't actually have a solution to that problem. One hack is to there's hacks, and I may just use a hack because you know what I mean? I may just want to see this actually work. And then, okay, fix the ugly little hack where we, check if it's a return and change it to a return near 0 instead of return near 8. I mean, there's ways of doing it. I can just compare a byte with 0 before I call the function there. And or change it, check it with 8. If it's 8, change it to 0. And then it's done. Yeah, I don't like that because it's, but honestly, it's not that bad. If that was the worst, we'd have to think if that was worth it or not. If it all works with the stack and everything, it's amazing. So, okay, so ink racks. So we go to the ink racks here, and yeah, when can I get coffee? That's what I meant to look up. I don't know. I distracted myself. Because again, we're under even though we're under lockdown, it's 5 in the morning, everything is loud. But it's Sunday, and Sunday things don't open till around 8 a.m., sadly. Is everything open at 8? 8, 8, 8. Oh man, I'm totally... There's probably some places, like I could go to the gas station. Oh, there's one that opens at... Oh no, yeah, 8 o'clock. Oh, actually 7 a.m. If I want, I can go to the near shopping mall and I could get some coffee. What time? Maybe Starbucks is open. That would be even better. Oh man, 9 a.m. What about at the shopping mall? Oh man, I think everything is 9 a.m. with Starbucks. It's not like early coffee. Oh, there's some that are open, but they're far away in the city. Yeah, in the real center of the city, maybe at 8 o'clock. I don't think any near me are gonna be open. I'm like really hoping for a coffee here. 9 a.m. It's like 2 near the shopping mall. Okay, everything's 9 a.m. near me. I've got like the option of the gas station. It's a good option actually. They have pretty good gas station near me. It's got a Spar Express. Okay, anyways, I think I'm just gonna keep working for the time being. I have to think because it's like, should I stop till I drop type of thing? Because then I'm pretty smashed and pretty exhausted. So yeah, okay. Thank you, Twitch, for exporting my video in a horribly unusable quality. I guess there's no option for the quality issue. Oh, I guess YouTube it has to process it. Okay, I'm wasting time looking this up. It doesn't matter. Check again in a few hours. 'Cause it's such a huge video. You can expect the quality issues. No, but I mean, it says it's published. This is weird stuff here. Like that was it. This little virtual machine toy here has gotten us to the point that this one's in 360p quality. Okay, there it explains it. So okay, that's done. It'll be later probably after it has time to encode it or something, or maybe not. Maybe it's just broken. After this ink, we see node adder loc minus dollar, which we know is not. I don't know what I was thinking here. What am I doing here? Okay, let's like the thing to do when you get stuck like this is to like start rethinking from the ground up here. Call loc p1 minus node adder loc will give me the number of bytes to get back to the node adder loc. Okay, fine. We've adjusted the racks. The hope is that racks here is correct. Yeah, I mean, like, what are the odds I can get this working with eyeballing all the code from here on out? So, okay, then we move. Of course, we've got the start topo offset, and that's actually pointing to an address, which is going to be where it jumps to. And then we add to the racks the node adder set loc. So we add some displacement. Again, relative, it's perfectly legit to do it this way. We could even combine some of this stuff. Right now, I want to just leave it spelled out. It's easy to combine. Then we move it. Okay, I guess we're pointing to the the move instruction for the jump. We're not actually pointing. We can look at it right here. So we're pointing, yeah, to this move instruction. That's what jump topo should be. This pointer should be set to. So it should be set. It should be a pointer. This should be a pointer to something, and then we get what's at that pointer, and then okay, we add 1 1, We're also inking the racks twice. Why on earth would we do that? Node header set look. Well, first we move the pointer, then we increment so that we can use that to load something else in. But what do we want to load in? Well, we want this function's node address. Now, we talked about how to do that before with the push statement here. So we've already got a solution to this issue that was reasonably good. And we used load effective address. So this node adder loc minus dollars is some relative meaningless thing. It's actually the surprising thing is that this is loading an address. Interesting that that would crash. Oh, Rax is what crashed it. Sorry. Yeah, I was going to say, okay, RCX is just a value feed. Okay, but this is obviously bogus. Let's change the columns here to being 16. RSP is D50. So this is what's the top of the stack. It's this address right here, which, by the way, looks like what we wanted. Looks like what we wanted. Then again, six one CO though. Zero two nine six. You know, honestly, the stack looks empty. But although this is a bad stack pointer, there's a lot of explanations for what could have gone wrong here. This is wrong. I know something's wrong, but I don't know if it went wrong where. Again, this is happening on the outer node. Subtract racks, inc racks. Again, I think we need to just look at this logically. Yeah, because we're comparing with a value that'll never happen. So it could have been popping values. I mean, actually, we're at the point where this could be working. Could be working, but this obviously doesn't work. But we already know how to fix this. Because what we want here, well, for the comparison, it's absolutely critical that we have this location, the call location. Okay, let's do that. Let's get this working the way we do the push here. I mean, that's all we have to do. It's going to be exactly identical code. And we don't have to fix anything. We don't have to fiddle with anything. Like, literally, we just get this push into the mix here and we're done. I know, this is starting to look kind of encouraging. I know it won't get to the end part because the stack's going to still get corrupted somewhere along the line. because we haven't resolved that issue, but we've talked about at least one hacky little way around it. I think there's a better method, but again, it's like one of those twisted things you have to think about for a while because there's several cases all coming in here, and you just want to make sure that each one goes through its own pathway without interfering with the others. So, where is that push? It's starting to get hard to find stuff. Maybe I've just been coding too long. I really need a coffee. I can wait 2 hours, but I don't think. Uh, wait, wait. I said 1 hour, right? Yeah, 1 hour. Yeah, just 1 hour. Um, yeah, okay. I can wait it out. Or I can go now. Two options. But I have to go kind of far to shopping mall. Okay, well, if I change my mind, I'm just going to go. Otherwise, I'm going to see if I can get this done. Really, really, really would be happy if this would actually just resolve itself right now. And this load effective address is going to be our key guiding point right here. So we know this doesn't work. So we just want node adder loc here. But the only way we're going to get it is like that. Okay, that fixes things. So the key is going to be this next one, though. Now, do we need to load the RCX again? We do, apparently. Or we could use the DX here. So this is changing the value here, which will be +1 +1. So there's no just single increment here. That'll never work. Just like it won't work here. It won't work here. So this is already our adjustment here because we're already pointing at the node address load. And here we're just going to write an immediate value, which we have to load, which we didn't have to load if we're going to use the CX again, which probably we should. I know, I feel like I just need to like correct all these later. Um, if this is not perfectly concise, none of it works, right? That's so ridiculous. I don't think we can compare, yeah, with a subtraction. Not really. If it was in an indirect addressing mode or something, maybe. So actually, as far as I see, we don't use the DX again. We use the DX for this start topo, but we're done with it already. And then the CX we're using for the node address location. And all we have to do then is add call loc plus node address loc, call loc p1. And I like that because then we don't have to do anything else here. So we're just going to use the DX here because we're done with the DX. And then we can say call loc p1. Oh no, we are going to compare it with just the cx. It's even easier. Oh, that's better because we've already subtracted off. Yeah, okay, I like this. Really like this. But again, the odds of getting it right are... Ooh, I just better be brutally careful with this because if we did this right and it's still going to crash, it's going to crash probably over in this part. And that means we're really, really... if it actually gets to this jump part, that's really encouraging because this stuff, as I say, is pretty straightforward out of everything we're looking at. This is like one of the simplest. Move, compare. Yeah, okay, this compare needed to be fixed. Um, it's set to use rip relative on this, and we are fixing it because we don't know where minus x will be. So that one had to be fixed. Unless we put x minus x as neighbors always, and we use some clever pattern trick. Um, Even then, it needs to be fixed. I mean, it can't be part of the blueprint because one will be odd and one even. And you still have an odd even parity to it, and so whatever. Yeah, okay, this. I'm good with that. The only thing I'm not good with right now is the stack. Everything else now is starting to look right here. Even this load effective address looks great now. This actually um, should use rip relative addressing to grab the address that we want here. And then we can put the starting address here at rax, and rax is node adder set loc plus 2, which is what we want. And then we can so we first adjusted it that we first get rid of the calling address because we never need to use that again, and then we can increment it twice. Then we can get the cx, and we're going to put there the value, which is some symbolic value we could even use x, but actually this is convenient in address. And then we decrement it twice. Now we subtract adder set loc as well. Again, we could do this all with less code. This is all just ridiculous. Here we have to do something, all right? But these could be combined, and these could be combined. Probably we should do that. Yeah, I'm kind of thinking, do I really want to leave this nonsense in here? Um, Actually, why am I... Oh yeah, I need to increment it here, yeah. And this has to... A double deck is probably more efficient than doing a sub 2. I'm not sure, actually. Maybe I should just write a sub 2 in there. Yeah, so here at next topo loc, yeah, we move that into this pointer, yeah. Whatever this topo pointer is. Honestly, this looks promising. I can't say too much is wrong with it. I could combine the math operations, but again, it's not like a priority. Uh, I can generate code pretty easily now. I don't need to do any offset calculations or anything. There were a few instructions that didn't compile correctly. We fixed all those, and we can see the rest are looking to be compiling correctly. It was just like two special rax relative forms, and I don't know why they didn't compile. If reported to Microsoft, Microsoft may just fix them, but you have to file a bug report to get those fixed. We're getting closer and closer to having a working solution. See if we can figure anything else out. That's painful. It got to FFFF here. Oh, load effective address. Oh, Rex. Yeah. 3C, is 3C the right address? It is indeed. That's what I like to see. The best thing to do at this moment in time is to actually start like maybe asking the question, has anything changed here? So it doesn't make sense to like investigate if we don't know what the value of start topo is. We've lost our context, haven't we? Okay, I have an idea. To save time with the debugging this stuff where I don't want to walk through a bunch of the code, we can just go down here to the no-op instructions. Because it'll only execute each one nodes once, so yeah, so it gets there. Now we can look at the stack, and it should have like a meaningful set of data on it. Yeah, that's kind of what I expected it to look like. That looks a lot better. So we're looking at what's on the stack here, and yeah, we see these ones, we don't care about them. We care about these. I see some addresses here, and it looks absolutely perfect. You have to say, I mean, that looks beautiful right now. The only thing is I see duplicates, right? Ooh, that looks terrible. Okay. 47C8 somehow on the stack twice. I think I can explain why. Wait, 47C8? Does that even make sense? It doesn't make any sense. 23A4, 23A6. Oh, wait. Well, I'm looking backward. Yeah, 23A4. BE and EC. BE and EC. It's here. That's right. Okay, EC is meaningless to us, and we just would subtract that off. That's why we pop first. Wait. Which one's meaningless to us? BE. Wait, it pushed and then it subtracted. Wait a second. No, it should have, it subtracted and then it pushed. Yeah, EC is the right one. So actually, yeah, it's going to get EC off the stack. I am kind of interested because though something seems to be wrong here. Uh, yeah, because I'm looking at the future address values and those don't make any sense because they're really far away. Of course, I really don't like what I see in that regard. Like it found a component with one element in the only the outer one, but where are all the inner components? Like, oh, 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 shoot. This isn't even a question. The stack's been corrupted. We can't call C. As soon as we call C code, it's going to corrupt our stack. Because we're using the stack in a way that we have to keep stuff popped off the stack in context. This is a problem. I guess we could use a base pointer. I'm trying to think how to do this. Oh man, the stack is causing huge problems. It's like I'm almost finished with this, but now I see the stack is corrupted. Anyways, what I see on the stack is a valid value, and it's the current node, so maybe we should fix this bug, but again, we can't fix them all because this is a special type of case, I guess. Yeah, the stack's corrupt. I know that much now. I know that much. Because stuff that's subtracted from the current location is very well possible. Now, of course, I'm thinking we'll just use the base pointer to store the true stack pointer. So we'll have like a I'm almost wondering if I've gotten this wrong in my model as well. Like, again, the stack was like one of the main issues I wanted to solve. So, I mean, there's going to be some way to solve this, but I have to think if we're getting conflicts in the way the stack is being used. This is tricky. So, there we go. Oh man, this is the type of problem you don't want to run into after working for 6 hours. Just realizing you've got a conceptual issue. Pop the racks at 7C. So this also shouldn't have happened as well. RCX is 8C0. Okay. Okay, I see the jump address there. It's fine. So it will change it to the right address, presumably. Yeah. RCX plus 2. I don't like what I see with RCX. Oh, no. Oh. This looks wrong. I mean, I see the instruction. What instruction should I see? I should see this 48. Jump topo. We should see a 48B9. Yeah, it should be here. Okay, I think I said it. Oh yeah, I know. I forgot to add the. Okay, that's fine. I know how to fix that. Yeah, we can fix it in C code. Okay, one thing to take note of. That's wrong. Consistently though. The real thing I'm worried about is the compare at the end. Mm-hmm. So now RCX contains 3C. Is that right? It's wrong. Oh, no, it's right. Yeah, it contains 3C. So the question is, are we going to get 3C in RAX also? No, we've got something totally wrong in RAX. 64889. Oh, that is totally wrong. Yeah, I see what's going on here though. Almost have to totally rethink the stack. That's why we're crashing. So this one is a simple one, I suppose. Somehow I jumped topo offs. But start topo should not be equal to this. It should be equal to this. Okay, but that was simple. Should point at the jump instruction, the right one. The question is, what's going on with the stack? It's the last thing that needs to be answered here. In fact, I don't see a stack corruption issue right now. I mean, I see a stack corruption issue, but I don't see an explanation for it. Because actually, the way we're dealing with the stack is we're leaving the stack pointer always ahead. It's just disconnected from its control flow order because we use jumps. But actually, there's no theoretical issue. I've rethought it. There's no theoretical issues there at all. There is an issue with the stack, but we just need to monitor it and watch it, and we'll easily figure it out. So actually, what we've done is basically confirmed that this code looks correct. Basically, actually, and we found one bug here, but that was a simple one. But I think the stack is correct. I think all I need to do now is look at the stack, and we will figure this out. So tricky, you know what I mean? This is the trickiest part right here. And we're going to see if we get anywhere. Let's see. Okay, are we going to get anywhere? Let's go in here. And now we want to kind of set the we want to look at the RSP from here. So we know as things go on the stack, they're going to be pushed from this D58 location. And the first value, we don't care. That should be like eventually we want to put a breakpoint here. And eventually we want to fix all the issues that are going to come about from that. But we should be able to get there. At this point, we should be able to get down to the jump. We should be able to get to the very last phase of this. Of course, we'll corrupt the stack if we call ones that have already been called, because the ret near should be 8 bytes at this point, not obviously not 16. And yeah, as I've said, even if we added to the stack pointer, then we'd need to decide if we should subtract or not. No matter what, we're going to have to add some logic in here. Or we're going to have to think of a clever solution, which is what I like to do, is think of a clever... There is a clever way, I think, of doing this. But right now, we've got the stack pointer tagged. So we've... Oh, no, we subtracted from it now. So 7F. Yeah, okay, so we see that the stack is good. Right now, it's good. Actually, since we're going to be subtracting, we want to make sure that we see more things happening. So we see that this is just going to be garbage. These are the values we want to look at, is the right side. So the first call, I mean, we know it'll change the stack, but we don't care. We're waiting to see this value get a correct value. So this, okay, it's going to change the stack. Oh. Well, it's never supposed to change anything at RSP or later. If it is, we're incompatible with C. Yeah, maybe. I want to actually do that again. I want to see a little more of what's going on. If it changed stuff on the stack pointer, that is so strange. It means that we need the shadow there, and that's the last thing we want, is to have to deal with these little stack details. Oh, this could be a real hassle. And again, this isn't an assembly language problem. This is an interop with C problem. So C8, there's our stack location. No, don't. Step in, don't step over. Oh gosh, what's happening now? Oh, I see. If we don't step in an assembly, we get to the lambda, which is fine. But the question is, why is it blowing up the stack? We may just look at one function and see what it does, because maybe it is assuming bytes in the callee. If it's doing that, it's really annoying. So this is what we want to see. We see the 0C call, and we see the old call from C. But let's see, the stack register should not change. It's C40. Yeah, actually, why aren't these docked appropriately? Yeah, that's better. Okay, that's a much better view. So we're looking at the stack pointer. Oh, C48. Okay, it's popped the stack. So the stack went back to C48. It went back to here. Oh yeah, that's actually okay. Oh, I forgot about that. That's the caller, and we don't need that one to stay on the stack. because it's not a node. And then we subtract from the stack pointer. Again, we reserve 8 bytes, so we're going to go right back down to C40. Now this 7F better stay here. So we're at C40, so we expect this to stay here as well. So when it does this call, C40, C40. Obviously, this is just defying logic. Next place you look is you go to the lambda here, and we're just going to look at the code. Now, unfortunately, this doesn't explain everything. Again, we have to be totally compatible here, and we have to understand. Like, maybe I just need to subtract and add from the stack and do probably like the 16 bytes subtract add will cause this corruption not to be occurring. But I don't. It should never be changing the stack in this direction. The only place to look is the x64 calling convention. Now, Microsoft has a document on this. The real question is about the stack. Obviously, the stack pointer seems to come back identical, but it's actually corrupted values on the stack, and it's like, I've never gone into this level of detail about how the stack works. And again, we're calling a bunch of STL code, but okay. Yeah, we've gotten to our function here. Oh my gosh. Move keyword pointer RSP plus 20. Okay, so what we're seeing here is like, it's not a big deal, but what we're seeing is that it's going to save the shadow registers as if the callee had to allocate the shadow space for, oh man, this is totally different than, how does this work? I see. So that's what's happening here. Of course, it's corrupting the stack. It wants those 32 bytes on the stack, so I guess we're going to have to give it to them. Actually, I don't see it modifying RSP plus 0, so that is weird. But I see it modifying RSP plus 8. Yeah, and then it returns the stack pointer. So the stack pointer is definitely preserved. Yeah, it uses load effective address to do the subtraction even. But even though it's preserving the stack pointer, it's yeah, it's expecting 32 bytes. This is not a huge deal. So for now, again, because we want to be compatible with C, the thing we're going to do is be careful. So we can just subtract ESP. Actually, it's not how they were doing it. They were using load effective address. Load effective address, ESP minus 32. Yeah, whatever. I don't really care. It's probably faster. In fact, we should probably, maybe we should make note of that. So we're going to give 32 bytes. We're going to call, and then we're going to take them away. And we're probably going to stop using this subtract from stack pointer, and we're going to just use load effective address from now on everywhere. Oh, no, 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 don't use ESP. Use RSP. Or we'll get real problems. Okay. Because it seems to be zeroing it if you... Well, actually, with load effective address, who knows? But, yeah, we don't want to mess with that. In case it's on a boundary or something. Okay. Maybe, just maybe, we can get it working now to the point where it crashes where I want it to at the return finally from all of the back to the very first call in this particular case. In other cases it'll return many times maybe, but this one only once, and then all the rest of the ones will be problems. But okay, take the blueprint and we stick it in here. Put like a little turn here, make it easier. Okay, hoping now. The good news is the modifying code seems to... Oh, no, 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 no. Good news is the modifying code seems to be correct, which means we're down to stack. 100%, I'm pretty sure the rest of this task is just getting the stack to work. Which, like, honestly, that is kind of the hard part. But the first part was the modifying code, the second part's the stack. But if we get the stack working, I think it'd be very interesting to profile this and just see what comes about. Wow, wow, wow. This is actually amazing. Of course, we're off by 2 here, and I don't know why that happened. Yeah, in this case, it's not jump instructions, but move instructions, but we are off by 2. That's amazing. It's honestly, it's truly amazing. That means we have the stack working. That detail needs to come into play in more places. It will crash again because we call back into C code in several places. But you know, we can just say shadow space. And we can go down here and we can just say, okay, we know the shadow space is needed, but we don't need it for the jump, only for the call. So in this case, actually, we can just say 8 plus 32. Oh, yeah, we don't want to use this anymore. We want to do it like this. (16 byte align and shadow space). Okay, this is really cool because this actually should do the job here. Let's just do this the faster code style. Oh, no, 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 no. We can't. I mean, we can, but we need to be careful because we're modifying this. That's like, for the future, we should do it that way. Yeah. We should do all of it like this. This is the correct. I mean, this is the way the compiler's doing it for a reason, because it's faster. Yeah, we should fix all of these. Again, I'm worried I accidentally made a bug here. That would be so stupid if I did that. Oh, oh come on. Another one here, right? Maybe we should just go ahead and actually fix these once and for all at the assembly level, because I'm worried I'm going to break something, and if I do, I want to fix it all once and for all. I don't want to keep messing around with stuff. So the first thing that I notice is some operation here is corrupted. Now start topo. Jump topo offset. Now that actually we didn't want, did we? Because it's plus size of byte plus size of byte. We said we don't want that. We want this to point to the instruction, not the address. Because again, well, both are important, but we have to choose one or the other, and we've actually chosen the other. Okay, I think we better fix this before we get too deep into this. If we're going to use the nicer format, and this should be very simple. It should just be a single byte change, actually. Yeah, actually, there could be something nice about this, but we do have to regenerate all the code and then make sure we didn't botch any of these changes. So here we go. F8 versus 08. Actually, it's more bytes. Can't possibly think it's better to use load effective address. Yeah, it's crazy. It's more bytes and yet it's faster. But for our purpose, I think we'll just take the faster variant. So the -8 is a F8, of course. Start putting comments in to just make sure we get these bytes right. Okay, so that takes care of this. So we can do this. We can get rid of the subtract once and for all. Do this like a normal assembly situation. And now we want to change it to an add. So the pop goes to a nop, and the F8 goes to a 08. That's kind of clever. I like it in a certain way. Yeah, and so we take care, and then we need another 32 bytes of reservation, but it's a temporary thing, so that we get, it didn't realize the caller. It said it's for the callee. The callee is using the caller's reserve. This is so weird. It's surprising to me, actually. It's surprising. But I guess the idea is that if you do it that way, you don't have to waste the bytes if a called function doesn't actually need this shadow space. It doesn't need to pre-reserve it. But actually, no, that doesn't make sense. It's almost like the opposite. Like, yeah, how the compiler could then optimize those calls. It would always have to give a shadow space even if it's not needed. But I guess it's just not concerning itself with these details. Okay. Yeah, we're gonna change this. Which means we move the byte pointer where? 1 for the nop. Where is the nop? And then we need to skip 4 more bytes. So we've skipped 5 bytes, and we want to just put a 0A. It kind of looks better this way. It looks more logical. Okay. And just to confirm that so I don't have to calculate the address, I'll just be lazy here and just let it tell me the offset. Although actually we're just adding what? 2 bytes, I think? Adding 2 bytes to the calculation. So yeah, 30 instead of 2e. So we added the 2 bytes. I don't know why it's 0, 0. There's a bug. There's a bug here. So now we hope we got that right, which takes care of the load effective address part. Wait, this is fixing this one? No, this one's the one that gets knocked. Peak red look. Yeah, that's right, because there's 2 different things. Where one, we're not changing the pop, but we're adding or subtracting. And the other one, yeah, that's right, because we get rid of it. Oh, this is so complicated. What a scheme. And then, yeah, the 90 here. Okay. And then here, uh-oh. Yeah, this is annoying too. Because since it's 5 bytes now, we're going to have to change this to a jump plus 3. I think we can just do an EB 30, 90, 90, 90. Let's try that. So it'll fragment the code again. Sometimes there's not an elegant way of doing it. Yeah, we deal with this, we deal with this, we deal with this. Wait, why are we doing... Oh, because this is the peak. Oh, that's a problem, isn't it? I know, this is why I'm saying I need to be careful. I'm like making a bunch of work with this self-modifying code by saying, hey, we can't just... we're using load effective address now. Now you can see these opcodes are all kind of similar, but at the same time different. 24 is the same, but 48 is the same, but there's 3 bytes that are going to have to be different no matter what we do here. We can do this, but then we need to make two 90 no-ops. So we need to add 5 to 2b or 4 to 2c, so we're going to get, again, 30. Actually, we already have the value up there. No problem, there's just lots of these silly instructions here. I'm going to say we're done. Again, doing all this so quickly, there's a good odds that I could have accidentally screwed this up. But I do admit this is better code. Just kind of quick review here to make sure that I feel like I got it right or not. Yeah, +5. I mean, it should be okay. I'm okay with it. Yeah, we still have to move the same move racks RSP for the peak. The peak hasn't changed. Yeah, we do this extra bytes previous to calling. Again, we just are keeping things aligned. And here, yeah, we also do it here before we push. We also do it here after we pop. Great, this looks honestly pretty good. And we do it here in some return cases. Get that blueprint. Okay, yeah, it would be nice if I didn't make any bugs here. Idea is to remove bugs, not to make the bugs. But that was a performance optimization purely, an assembly optimization like the way compilers do it. And why that's faster? Well, there's some technical reasons under the hood in assembly language why using load effective address is faster. But it is a highly optimized instruction, and it works a little differently than add and subtract. Probably what they've done is they've laid real estate down on the chip to do like some kind of special 1 byte and maybe some special carry chain operation. Whereas add and subtract, they have to do the full carry chain. So I'm pretty sure they've just like, you know, optimized this single byte displacement. I'm pretty sure it's a special optimization in the hardware to save a clock cycle or two. Hence why we see that. Okay, what are the odds that I didn't break things doing all that? We'll see. Not very good. Apparently not very good odds. Well, I have no idea what just happened. Oh. It got to the jump chain. Huh. That's amazing. Honestly, it's amazing. It looks like I came out bug free on that, and we're finally at the jumps. Okay, this actually we can finish this. If I finish this, it's a celebration. This is a huge effort that this has entailed. Working hours here. Get something. All right. Let's box here. I need to get something. That's cute. at least this isn't everything, because there's so many practical details here. But, yeah, it's just so many practical details when you have to do this stuff that is not the end all be all of this task. But it's a very good step in the right direction. So I'm going to carry on now. I'm going to finish it. I'm not sure what I'll do afterwards. I think I could set up the but this is being finished right now. End of story. So the way I'm going to go about this is look at what we're comparing here. Now, we said this was RIP relative. And so this should be okay. Actually, I don't see any problem with this being RIP relative, but it's got to be relative. Right now, it's the current nodes. Node adder set loc +1 +1. Yeah, it's the current node. It's actually getting this value here. +1 +1 is $-7. Assuming that compare is 7 bytes, which I'm pretty sure it is. This has all been checked before. So that compare instruction is indeed 7 bytes. So you see FFF1, that's fine. So all we needed to do was take that FFF1 and offset it to the minus x1 relative to x. Clearly I didn't do that. Clearly I didn't do it correctly relative to another. So what are we doing in here? It's this check same SCC offsets. What I'm adding to it right now is an absolute address, not a difference in addresses. And we know we want a difference in addresses. So it'd be this minus something. And instead of, and don't we actually have this? This is times I. And somewhere we have all of this, right? Base BP. Doesn't like that. I'm getting my types mixed up here. It doesn't really matter. I mean, size t should be the size of a pointer. Might want to be careful with that, but at this point, I want to see what happens if the jump chain starts to work. I think it worked. I think it worked minus the stack. Wow. I think we're actually that far into the task that it's going to work. So here's what I'm going to do. To quickly check this, we can just put a breakpoint at the jump chain. So when we get in here, we see here's the jump, RCX. Wait a second. Yeah, that's the jump, the start of the jump chain. So we put a breakpoint there, and we get there. Wow. Now, 794. Now, this is where we can actually go check that we did this offsetting correctly. Uh-oh. I'm not sure even. I see 48B8, and now I see this. It looks absolutely perfect. JBE. 3c. But why is it jump if below or equal? That's wrong. It should be jump if equal. How on earth did that happen? Yeah, I mean, jump if not equal. Or is it the same thing? Seven five. How on earth did that become a 7-6? Well, equal, of course, works here, but we can't do jump if below or equal. It's so weird, too, because, like, how on earth would a 7-6 get in there? That is just... That is inexplicably strange, except when you realize this is supposed to be a 4-byte value here. Because we're saying we can use rip relative because we know this byte chunk is going to be within a 32-bit range of each other relative to itself. If it wasn't, it would make things really complicated. If we were doing a graph that big with 8 billion nodes, we'd have to rethink all of that. But we don't for this because I don't know why I said this is a pointer. This is clearly a 32-bit size here. Okay, but okay, so we know we need to fix that. Again, it's like, let's fix two bugs at once. So, okay, it still did the right jump here, which is to go to oh no, a jump if not equal. It should have actually gone to unsat immediately. Should have just jumped. It should actually, this is where if the stack is okay. So actually here it's going to like try to set the solution. Okay, I mean, I know that's wrong. Jump RCX. Cool. So it's going to the next one, and we know they're all... Oh, wait. D6. Yeah, it looks right to me. It looks right. It's because it's... yeah, it's a negative value. Oh gosh, and this is the carry bit. So actually, it's kind of working. In this sense, it truly is working. Let's see what this RSP is. It ends with an 8, but we know it's messed up now. Or do we? I'm pretty much, I know it's messed up, but I want to actually see that it is messed up. The jump chain works. This time it got jump if not equal, because it's still negative. Yeah, okay. I mean, but I know the problem here. It's all zeros for the 4 high bytes, or 0, 0, 0, 0, 1, I guess. Or actually, no, it's all Fs. It's all Fs, but it ends up just causing a carryover of 1 bit. But we need to fix that. It's supposed to be a pure 32-bit subtraction. I guess we have to hard code on signed long there, or anything. It doesn't matter. Signed long. Signed long is probably better. Oh, here it got to unsat because it actually said, I did see, of course they're in the same, so it works. I mean, the jump if not equal does work. It did find that it is unsat. The problem is when it jumps to this unsat function, the stack is probably corrupt. So 888. And now it's going to just crash out because the stack is corrupt. Anyways, if we fix the stack, this works. This whole scheme will work all of a sudden. Whew, that was tough. And we're not out of the woods yet. We still need to do one more thing. We need to fix the stack, and then we have a self-modifying code, pure assembly model actually written. And we haven't even done 32-bit, but 32-bit is generally easier, but it'll still take some time. I mean, I don't care how clever you are, it takes time to do this type of stuff. Especially since a bunch of the instructions will be quite different. And I think right now I would do two different ASM files, another ASM file for the 32-bit model, and if I want to macro merge them, I do that at the end. Because there's probably going to be enough differences in addressing and stuff that it's going to be, it'll be complicated to say the least. So, okay. This one is easy. Now it should complain. All right, so I want to check the stack pointer now because everything is decided right here. So the stack pointer right now, 9C8, is what we want to see right here. It's 9D8. Still got jump if below or equal. Okay, let's keep on fixing that. Oops. Yeah, that now it should complain about a size. Yeah, okay. We don't really care, but probably we should just cast this at some point. Yeah, it even says it's size t, because now we're doing a pointer subtraction. We're just going to say, we know this pointer subtraction is 32 bits. Thank you, compiler. Okay, so again, the problem we're going to have right now is that if we can't explain what's going on with the stack, we're in some big trouble. So what we'll do is, we're assuming it all works now. I think we've seen enough to say that this code works perfectly. We've basically got now an 100% coverage, and we've got only the stack to resolve. Actually, not bad. It's my second 8-hour session probably is to get this working. It's 6 hours 30 here, but I think we're going to get this working very, very shortly. So okay, the stack is BA8. And what we'll do is we'll just start putting more breakpoints to see how messed up it gets. Another option is to just save the stack pointer. I don't know if that'll work, but we don't use the base pointer, so I was thinking, we'll just save the stack pointer. That might be, I have to say, that sounds like a really clever solution. And there's even yet another option, that's to push the stack pointer and just pop it and say, okay, we know the stack pointer is going to be messed up, and we just don't care. But the problem is this whole 8-byte alignment stuff is going to also get wacky if we don't do this cleanly, and that's why I'm like, oh, maybe have to change the returns. But we should, after we've moved racks this value, it's easy. We can compute we can do everything without actually changing the the blueprint at all. It's just the size of this will change, but the one offset we need is already done, so not too difficult. I think I can get the whole thing then actually working. We'll see. I mean, just trying it on the first topological sort, there could definitely be more bugs. So let's check it. BA8, BA0, that's a big problem. And then the other three are going to add. Okay, that's the problem. So these three adding, I understand. I knew about this problem. But the first one is really suspicious. I know why it's happening. It's because it's adding to the stack before it returns. And the other three are not subtracting too many bytes. We have one adding too many 8 bytes, and they have the other three, or not. Oh wait, the first one's subtracting 8 rather, I guess, and the other three are adding something on those lines. Yeah. Actually, we can just walk here. We can just walk over this. So BB0, BB8. Yeah. So the adding, the first one subtracted too many bytes. The next three added too many bytes, and obviously we need to align all that. Yeah, jump if not equal. So this is immediately should call unsat. Yeah, that's right. And hey, if this stack was like BA8, I think it would work. Nah, that didn't work. But it's effectively working, and we're down to the stack issue. I guess the stack has been corrupted after this first call. Yeah, why is that happening? Everything works perfect with the stack. I shouldn't say everything, but it looks like a lot of the cases are working now. There's like 3 stack cases that maybe one isn't tested yet, I guess, the way the components work, but still might work. Maybe. So we've got the stack here is 898. And so we want to make sure that return address doesn't ever get taken off. If that happens, then we're in a lot of trouble. Okay, B38. B30. So it should be B38. Okay, and then it's of course going to blow up the stack. Yeah, okay, so the first problem is why did it subtract too many bytes from the stack? Well, I think we know why it did it. No, that's not the one. I had forgotten about this case too. We have to like solve all of these cases. Okay, I know why it's doing it. So right now we want it to add 8. But what do we really want to have happen here? This is so confusing in a certain sense, but not really. Uh, I know I just want to glue this last bit together. I think the solution we're going to use is to just add 8 bytes to the stack, but then we get this whole alignment issue coming right back into play. So I whatever I do, the problem is we're unconditionally moving. Oh no, we're not. We're not unconditionally moving. We're only doing it. Oh, but we do it always. And we may even interfere with our own node. The current node that we're processing, yeah, it's gonna change it to a yeah. Oh, it's no. Wait, where is the right one? Still not looking at the right place here. Yeah, here. Okay, so we're changing it to a no-op. But we're gonna end up changing all of them to a no-op then. So that will never occur then. Yeah, but it's only because it's got to be called, and if it's called, it changes it to a no-op. Yeah, but it's some that that's it. That's it. This is very tricky. If I can just come up with a scheme that handles all the cases, it's finished. But it's literally it's just around like maybe this location and maybe here where it's calling. Uh, I've already figured out that we could set this to um, we could detect that this is a subtract. What do we change it to? A return instruction. So we could detect this as a return and always just change it to 0 from the call blueprint area. Then that's probably what I'm going to do. But that'll only solve some of the problem. It won't solve the problem that we're messing with this this return address loc. Now, do we even need it? Is kind of the question I want to be asking. Yeah, because we should have added 8 more bytes to the stack. Yeah, we needed to add the 8. Yeah. Because we need to preserve what we did up here. Yeah, so it has to be added. There's no choice because we do this -8 here. Sometimes we're doing a +8 there when we peak. Oh, no, we don't do a plus. What do we do? Yeah, +8. We change it to +8. Oh gosh. I see. So we have the -8 here already. So we do a +8, and we want this to be a no-op. So there is only one bug here that I see. I see the only bug is that we don't want to do this for a node that's already on the stack. Because this code hasn't yet executed. Yeah, it's this one. This one is definitely, this is a poisonous type of a statement. We only want to do this again. One idea is to not change it for the other node because it hasn't executed yet and we need to keep track of what's on the stack. There's a state issue here. And the problem is this is not a stateful way of handling it. The assembly code modification is okay. Jump +3 is fine. The problem is we're doing this totally incorrectly here. So this is going to be... We need to think right now. Right now we want to know, were we called? I mean, that's really the criterion, unfortunately, here. The criterion is really, are we called from another node, or were we called from the call blueprint? If we're called from the call blueprint, we want to add 8 to the stack. In fact, not only do we want to, we have to. But if we weren't called from the call blueprint, we definitely do not want to add 8 to the stack. Because we've already done that here. Wait a second. So I have to think, because it seems like we've got this idea right. This should always add 8. Because, yeah, it needs to save the return address if it was a peak. And if it was a pop, no, if it was a pop, it doesn't need to do anything. It could subtract, and then it could add again. That peak case. Then why can't... Yeah, actually, I'm starting to come around thinking about this and saying, maybe this actually doesn't belong here. The hope is that we can just put this over here. I doubt it'll work, but the hope is, yeah, that only if we peak. Wait, if we pop, oh, then I see, we add 8 here. But then why do we do that? That actually raises a really good question. If we pop, can't we just actually not do anything? Yeah. No, because we need the stack aligned. Ah. If we pop, we have to save 8 more. No. If we pop, we should actually add 8 to get it back. Yeah, that's right. If we popped. So push or pop, or peak or pop, we actually, I think this looks right to me, that we always want this to be +8. We can always check if the node has been called already. I don't particularly like it. I don't like it at all, but it would work. I mean, it would give me the criterion I want. Because we can check the first return instruction and see if it's there. Just like we can do everywhere. I mean, I really don't like that. Oh, but again, I could make it work. Kind of like, okay, I have an idea that would solve all of this. And so we could actually see if this code really will end up working. Because it would be so, that would be so cool. Um, yeah, that's like the workaround is to say, okay, if the uh, function does not already have the return block over there, then we'll add this nops in there. But if it's in process of being called, then don't bother doing this because it's just counterproductive. Okay, so let's think 3 pathways. The first one we have to subtract 8. The second pathway, where it comes here, we subtract 8 preemptively. So we don't need to subtract 8. Yeah, I'm kind of like, there should be a way to unravel this in a better way. But in this method, we've already aligned the stack. So in this case, the stack is already aligned. So we unalign it, realign it. No, wait a second. I know, I basically just want to redo this stack management code because once it's done, it works perfectly. But there's several issues to it right now. If I didn't have to subtract 8 here, that would be nice. But, yeah. That actually sounds like the solution. It sounds like we can simplify all this, and that would be beautiful, and I don't need to modify anything outside of it, and oh, that would be just so nice. Yeah, gotta get my head around this concept. Okay, so we come in unaligned, and then we pop. Okay, I think I know what to do here. I almost feel like I've just allowed this to be an overthought issue, right? Stack pointer's 8. Okay. Stack pointer's 0. We're okay, but we're going to take it off the stack. Because we're going to take this return address off of the stack, in fact, we don't even need to. We could actually use a return instruction. We don't have to use jumps and all this extra self-modifying code. These are all options. Again, it's nothing to do with the model in general, though. But yeah, if we take it off the stack, we're unaligned, so we reserve the stack again. Yeah, so we're aligned now. And you can see this is just going to 8, 8, and then back to 80. Okay, so unalign, realign the stack. But now we have to add to the stack 8 bytes before we leave. Absolutely has to be done. But if it comes from the call, so at this point, the stack is aligned. So we need to be aligned for the code here. But we also always want to be unaligned when we call ourselves. We always want to assume the stack is going to be either the same 8-byte. It's amazing. I'm fighting so much with this little 8-byte game. In fact, if I took it out, it probably would just work, and we wouldn't have to worry about all this. But this is kind of life right here. I just kind of want to solve it because this is like general best practice. but I'll tell you. So if we subtract here, we're aligned. Now we're unaligned. We call, we're aligned. That just doesn't seem right. I said when we call, it should always be unaligned. It should do it properly. So the first big question I have is then why are we even doing this? This seems absolutely pointless. Let's actually verify that that's right, that I'm violating the assumption. Again, it's worrisome because if I change anything, probably things will break again. But 80, and now 78. Boom. But I know that for sure there's a problem with this idea. This is causing some serious issues. We don't want that there. First thing we know, we don't want to do that because we want to go back into this kind of misalignment. But now we want this to add bytes. Why do we want to add bytes? Why not subtract bytes? Why are we... Oh, because, if we pop, we wanted to add the bytes. But we don't need to. If we pop, we're done. We're aligned, and we don't need to ever think about it again. So we don't need to add bytes. So if we're going to pop... Oh, yeah, we do need to because... no, we don't need to do anything. Yeah, I keep flipping on this. No, this... if we peak, then we need to subtract an extra 8 bytes. If we pop, again, this code is safe to change because it would have already executed. So whether we're changing it in a node that's executed or not, it won't happen again. I need to think about this. This is so tricky. I'm going to be fighting with this stack until it works perfectly. Perfect alignment. Perfect 16-byte alignment. No games, no issues. We're getting this done. All right. I think the next step... I mean, at this point, it's just logical stack stuff. There's no tricks left. It's just one issue, and I think the whole thing will work. Could be another bug or two, but we'll see. If it works on the large SAT instance, it is probably right. Okay. Next issue. We definitely did not want this, but we definitely do want this, but not always. If it peaks, we want... If it pops, but if it peaks... We need to actually take... we just need to take... And we subtract 8 bytes. That's right, we subtract 8. So peaking needs to take another 8 bytes that will never come back with a no-op at the end. Okay. I'm going to redesign this right now. This can now be a C3. and a byte pointer. Okay, so we've got the C3 in here. Now we're going to do the next, so that will actually change this to just return now. That actually fixes the calling function too. We don't need that. This only needs to happen on a peak. On a peak, we need to subtract. And we don't want to add back. Yeah, we don't want to add back on a peak. Good, because this is much nicer. Finally, the pop case, where we're actually going to call it in here, and then what we could do is we could just knock this out and say if it pops, we don't even need to fix the stack because we're back in alignment. Wait a second. Oh no, we did need to be into alignment. Oh gosh, that's the problem. When we call this, we're already aligned. Yeah. Well. But what if we aren't in alignment? Would it be simpler? I think it would be much simpler. So you put it back into alignment. Pop, we're out of alignment. We're in alignment when we call it. So we need this. We need to stay in alignment when we call it to be consistent. Yeah, that's why we did all this. So, okay. So if we peak, we stay in alignment. And we don't want this if we peak for sure. And if we peak, we knock out the, well, everything. We change it to a move. So if we peak, we're doing the right thing. The peak case is definitely satisfied correctly with this code. We could even move this into the peak case. And so I almost kind of want to do that, but the next question is what we do, and this is the one that where it's going wrong. And if it's already called it, we're going to take 8 bytes off, mainly because we're assuming that the extra 8 are here. And finally, if, oh, this is such a tricky little issue. Finally, if we just pop the address off, that actually it takes us out of alignment. go back 8 bytes. Well, then I don't see a good solution. The easy solution is to just put a compare instruction here. Yeah, the easy solution is just to compare and jump. So if it's already on the stack, it would actually have already changed its own return address. Because once the node calls itself, or is called, and it accepts itself, it has to have somehow been put on the stack. And at that point, we don't actually want to nop it out anymore. Yeah. And of course, there's some of these things are not optimized, but to me, this actually would work. So my first instinct is to just try that. And yeah, we're gonna have to do the same thing as a fixing in the code blueprint, but we're done then. I don't like it, but if it works, it works. If it works, it's finished. And we can think about how to fix this detail. Turns into a deep think on how to do this. Because the problem is, as I say, the real difference is where we got called from. All right, let's see if it works. So our stack is 8D8. I'm still at 8D0. So I'm looking here at, yeah, it's comparing racks plus 10. It should work. This should work. If it's equal, we don't want to do this. All right. Oh, it's this nonsense again. Yeah, this is madness. Back to the racks addressing issues. Oh, I have a spurious move instruction here. Yeah, but that's not the problem. So we want to put some db define bytes, this, 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 and then we want C2 again, we're just fixing compiler bugs here. Not much else to do about it. All these racks addressings are causing problems with the immediate argument. It's simply not emitting the correct code. And so we can look here and see C208. We can just fix this by hand. Looking for 8178. Should be C208 0090. Okay, so that was it. Probably that fixes this part. And if it does, then we can finish this. I'm not going to say I'm happy with this solution perfectly, but it's not too bad. I didn't check the stack. I think it worked. AB8, it looked like it worked. Oh, come on. A18, A18, beautiful. Now the other ones are going to screw the stack up, but it's fine. We can just fix this right now. Okay. Whew. I'll tell you. Tricky, tricky code, especially when the rack's relative addressing isn't working. I probably am going to go to Microsoft now and actually submit a bug report. I'm going to do it right now. God, how many examples of this? Somewhere there's a check, a send bug report, send feedback, report a problem. Oh, I'm not signed into Visual Studio. That's weird. That's being taken care of. Okay, good. My Microsoft account's up to par here. Now we can send feedback, report a problem. Oh, it takes me out of Visual Studio to the web anyways. All right, I'm just submitting a bug report, so bear with me. This requires a little bit of thinking about trying to say this concisely so that, who knows, maybe they actually fix it. Okay, I finished it. I now have opened an issue. Okay, that was that. I submitted my feedback to Microsoft, and I hope at some point they are going to fix this issue. In the meantime, let's finish the job here, because the only thing left to do is to... I gave them all 5 examples I have. Said I think it occurs with the word pointer too, as I think we saw that before as well. I did notice I had some comment wrong in here. These should have been byte pointers, not double word pointers, or word pointers, but whatever. The code is obviously matching this one, and I'm sure they are correct. The only thing I am having trouble with right now is that what we need to do is we need to knock out this C208, and we need to turn it into a C3 or a C200, either way. So if we see this is a C2, we need to do something about it. So we can just, actually, we can use node adder low plus 1 plus 1 plus 8, 1 plus 1 plus 8, whatever we do before. I think we can reference it from another function. So we can say compare the... We could do the D word pointer. We can... Well, it's going to be the same problem. Actually, we can just... Oh, no, it won't, because we're not going to... Oh, it will, because we're using Rax relative. Yeah, anywhere we use the Rax relative. So if it's the same, we can just copy and paste. Oh, isn't that nice? It's exactly the same. I think we'll just move a byte there then. Yeah, we'll just change this to a byte pointer. So that's going to be a byte pointer, and we're going to move C3, and we expect that this won't work in terms of MASM is bugged. Oh, so it doesn't like node adder loc? Yeah, I was thinking the labels might have some kind of a scope to them. Well, since this is all relative anyways, I kind of like using the fact that, you know, if we change things, it might be compatible in the future, but we can also check what happens if we get... Maybe that's also influenced by the pointer offset. Yeah, who knows? Right? If it is, that would be interesting as well. Then we should have sent that in with the... Oh, look at that, it worked. Oh, that tells us something, though. That does tell us something. Oh, that's interesting. So it only happens if you're doing these offset differences. This is why Microsoft never found this. Oh, that's what's corrupting it. It's the fact that I'm doing this mathematics over here. Still, it's a bug in the assembler. It is still definitely a bug. Because otherwise we can't do... We're not allowed to do these subtractions. Isn't that interesting? So we get the right code here? Yeah, we do, huh? Oh, Microsoft's going to have themselves a little number with that one. But it's true, their compiler's botching out. I'm doing a pointer subtraction, and it's called... Oh, so I should probably mention in that bug report, it's the pointer subtraction. That's, you know what I mean, just to be complete. Oh, wait, we somehow needed a jump statement. Okay, now we're starting to hope that this will actually work. Huh, it's making me use a different Microsoft account. Well, if I can't fix that, then what can I do? Huh, weird. Okay, so the pointer subtraction is causing the problem. All right, let's see if we can actually take care of this once and for all. It's like the big countdown right now. Time for a drum roll because I think we've solved this. Oof. Took a long time, that's for sure. Was not easy. And we don't even know yet. This is just a hope right now. If it works, though, that would be really fantastic. That would be amazing. Constructed all this special code to do all this stuff, and now we just want to see it work. Uh-oh. Something went wrong here. No, actually, this is exactly what we expected. Okay. Jump if not equal. Okay. I mean, aside from this stack corruption issue, Oh, access violation. Stack corruption, eh? Two, -1, 3. Wow, I came back with a solution and stuff. And again, somehow, again, this is actually going to be. This is tough. I mean, at this point, I'm not like doing anything too crazy because the stack pointer doesn't change. This is interesting. It's very interesting. I have no idea what would make it think there's stack corruption. RSP is 940. RSP is 940. Wow. What makes me think should be checked is the stack pointer here, that nothing changes in the future. Oh, wait a second. We already know what the problem is, don't we? Okay, I know the problem here. The problem is we didn't reserve a shadow space, and the problem is the calling this function didn't reserve a shadow space, I suppose. Maybe. Actually, that might be the problem. We have to look at the disassembly to determine that. I don't think the stack's going to change, but we'll see. If it does, it's probably shadow stuff. Okay. I did see some change. 9FB0. Did my code do that? Or... I have a feeling there's like a tiny little detail here. Tiny detail. I mean, yeah, the stack, it's what? It's subtracting and then it's writing the values, as far as I remember. So this is the value at the top of the stack. Okay, so what we should do is take a look at how this call is being constructed here. But this function already has got a shadow space, doesn't it? So it just calls it. It doesn't do a thing. And it shouldn't have to because it already has a shadow space. But how does it know where the shadow space is a good question. All right, so what we do is we take a look. This type of detail can be very annoying to figure out. It's again, it's like some incompatibility, and I don't know if there's bugs in the code right now because I saw the values coming out of the sat solver. It looks really promising, is all I can say. So I'm looking again at a lambda function just as an example, and I see this prologue here. It's saving two values into RSP plus 8 and plus 10. Yeah, I assume that's it. Loads the base pointer RSP plus 20. Again, we have to kind of look at just what goes on with a normal calling convention here. That's it. So the question is, where is this shadow space coming from? From its caller. So, this is weird. Yeah, I don't know how to. If there's not an easy way to trace back this stack corruption. The easy thing I see to do is to take a look at what the stack is here and like see if it changes or where it changes. So RSP is A70. Now it's going to be A68, which is our final return. So the question is, how on earth did this change? It doesn't make sense. Oh, we're trying to use this as a return? Yeah, but it's the same. I mean, presumably this is the shadow space. Yeah. Okay. So far it doesn't look like it's changed the stack at this point. Okay, I mean, I see it changing the stack. I know, I can understand that must be where the corruption comes from, but I'm having a hard time saying exactly why. So here's what we can do. Let's call unsat, just for the fun of it, to see like what the construction difference is in the assembly. Absolutely no difference. I mean, absolutely no difference. Absolutely not. Thanks. Wait a second, that was weird. Oh, hold on a second. RSP changed from F30 to F30. Okay, I mean, it didn't change. Okay, that's good. So 9FO. And it changed some value on the stack. But around P code block is such a weird situation. Okay, let's go look at P code block. Let's just do this and see if it's corrupting the stack anyways, if it's a separate bug. Aha. Great news. Okay, great news. This is not an assembly language bug. It's a bug with the C code. Okay. Huh. Somewhere we're dereferencing a pointer incorrectly. Let's just start commenting code out. Like that huge for loop. If I don't need to look there, all the better. Otherwise, I will look there. So that's where I'm expecting it to be. But I'm wrong. Good. That's great news. Fuckacade. Fucker. I believe he goes by that name of Michael. Fucking. Huh. Alright. Solution. So interestingly enough, it got corrupted in this routine, which is just returning some lambdas, and I can't fathom this would be the thing that corrupts it. The other option is to just take out some of this kind of code. And see if it actually isn't that code, it's just hiding it or masking the error. Yeah, okay, so it is. Okay, great. So obviously one of these assignments or something is messed up. Which actually is interesting because all the assembly code where you would have thought there would have been a problem turns out to work perfectly. This is interesting. Wait a second. Man, this is so weird. I don't know. I imagine. And it comes down to a C bug. It's just absolutely ridiculous. Okay. So there it is. It's here, and there's index, and there's some other values. Because it says it's near to this. Whoa. Okay. This is going to be solved very quickly, I suppose. Why on earth do I have this here? Because I'm patching. Okay. I'm surprised it could possibly work. It's not crashing, but it's not working either right now. Oh, because we don't even call it. Ah, bummer. Okay, so it can do the unsat case. but the sat case doesn't work. But I think I know what's wrong. I think it's the final jump instruction, which never got tested here. So actually we can close this up because we figured out what the stack corruption bug was. Took a while, of course. It's kind of like one of those, you don't really have, it's around this area, but you don't know what pointer arithmetic where was causing it to be around that error by coincidence. Uh-oh, that's not what I want to look at. Oh, yes, I want to look here. Okay. Okay, the good news is it's this compare instruction. And we're seeing F488 here or something. 339. Yeah, so somehow that. Not funny. Not funny at all. How on earth? So we know the problem is here. It's this compare instruction. Isn't this subtraction backwards? This, I guess, yeah, we don't really know that this actually works. In my opinion, that was backwards. Yeah. Oh, doesn't look good either. All right, probably the same exact location. Nope. All right, but probably we're getting to the. I have a feeling this is going to be of the last bugs now. Like, last details, even, to having this whole thing working. So let's just see if it gets to the jump, which it does. So now I see 0404. I'm imagining this is a correct address. I have to confirm it here. No, apparently not. Well, let's go back and just look at it in memory. Looks good to me. It's a valid address. 48B8. I mean, this is exactly like one of these. I don't know why it won't show it here. It's just the disassemblers being silly going backwards. Sometimes it has trouble with that. Anyways, yeah, it's not a perfect disassembler for sure. So, anyways, that worked. So the problem right now is that it's not getting all the way uh, through even the main code. So again, it gets more complicated as we get more realistic strongly connected components, I suppose. So kind of a question would be like, how many is it getting through here? Oh, I see. Actually, I see where it is right now. And it's misaligned, or not misaligned, but it's like, it's call racks, move a byte pointer C3. Yeah, look at this. Look at this. And it's totally confused here. See the C208. So something went, so something's off here. So I see the call racks. I see the move C3. Let's just check that out. Yeah, I'm agreeing with this. Because it's got an FF78OA, which doesn't make any sense. This is strange. When I index the nodes, I hope they're zero-based or something. It shouldn't be a problem like that. But yeah, I see that the move call instructions, they're botched somehow. One of them is. I don't know, the first four are perfectly fine. And then I see a move, and instead of a compare, I see an FF 780A. I don't know how that happened. In fact, everything's right except that FF. So strange. But we never are moving FF anywhere. Yeah, this is strange. This is truly strange because it seems like this came about already. So we have to kind of like debug this. Fortunately, we're not debugging assembly. We're just debugging like construction code here as to why it did not construct the call blueprint correctly. Okay, I don't want the zero case anymore. Let's just take that out of the test. Start with the one case. No, don't recompile. So if I look at P code block in the disassembler, well, we can just jump to it. Wait, it's not corrupted right now. Wait. That's weird. I know this is going to be tricky to figure out. Okay, it has 4 values. That's right. It's giving an answer that looks right even. Oh, okay. Yeah, I don't know what that corruption was. Maybe Uh, the jump or something is wrong, and so that's why it just jumped somewhere that was illegal. Again, this is very tricky code, and if you make one mistake, you can expect. Yeah, it's definitely, there's no construction code problem. We expect it's going to call for or eight times. So there should be an 8 jump chain here. One, two, three, four, five. Now this could be stack corruption. 6. Which case I should have looked at the stack pointer, because I'm not going to solve this if it's stack corruption the way I'm doing it right now. Is this the last one? Oh, that's where, okay. Okay. Is there stack corruption? Because it's supposed to jump to sat. My guess is stack corruption. And it does jump to sat, just with a bad stack. So the easy way to look is we see RSP as E58. I didn't see stack corruption. It means I have to follow this jump chain again. So this is 1, 2, 3, 4 nodes, 5 nodes, 6 nodes, 7. This is the last one. So now we want to see where it's going to jump. Which it should, actually this should work. Or did I miscount? I think I miscounted, but okay, so it's at this one. Why is it jumping to the RCX? Not the RAX? That's totally wrong. Okay. There's a 1 opcode problem here. And it should be FFD0, the last instruction. Wow. Tell me it works. No, FFE0. Not E1. Yeah, I should know that. Okay. Usually AX is the 0, and then CX is 1, and I think DX is 2. So I want to know the details of how the layout of the instructions are. The accumulator is the prioritized one, and then the counter. Okay, I think we got it. Wow. Let's see. Well, something's still wrong here. This is so annoying. We're right at the very end of the task. This is it. I mean, if we get this one working, it's done. We have the whole thing. Oh man. Been doing this for 8 hours now. This is about the limit of where I'm too exhausted, but not yet. We're gonna finish this. We are definitely finishing this. Too far. To allow any tiny corruption or anything into the mix here. Let's see. One. Oh, but this is weird. Okay, I think I know the problem. Because next topoloc is set wrong. Okay, let's just we have to just recompile because the offsets are all going to change now too. Okay, that's simple. Whew. Man, this is difficult. I'm kind of lucky I've gotten this far, spotted all the things I have. I mean, if it does work, it'll be really, really cool though, so. As I said, I think we have it now. I think the whole thing will work. No way. Oh. So it makes it through the single solution one. Fine. Now we don't check if the solutions are valid. It's easy to check with a boolean equation. Again, that's a very polynomial time, linear time algorithm to check that all the clauses are satisfied, but I'm pretty sure they are. So now we get another bug. Oh, that is looking... Oh, okay, and it's unfortunately it's in this place. It's in this stuff here. The Rax is wrong. Oh, looks like we got a stack misalignment here. I'm wondering if I can finish this now. I'm pretty tired, and I'll tell you, this has been a lot of work, and we're basically at the end now because we've gotten it we've gotten it to work for the single, the unsat case and the sat case, but we haven't gotten it to work to the case where there's multiple strongly connected components, and already I'm suspecting any number of problems could be coming from this part. The fact that we got a stack misalignment gives me a strong hint as to what this problem actually is. I don't think this problem is coming about except because of the peak pop area. I'm almost certain it's misaligning the stack there. And again, a single misalignment, it'll cause a crash, basically. We can't be off even a single bit. The good news is, if we solve this, I'm almost sure, by the time you solve the 3-solution one, the one with tons of solutions and lots of components, no problem. At that point, this is enough to hit generality for us. But now there's a lot more nodes. There's 16 nodes in the graph because there's 8 variables here. So, is there any quick thing we can look for here? Again, we know it's working in other cases, so the fact that it fails there just tells me that we see that it got a bad stack address. We just know that something went wrong with the stack here. It might be hard without actually starting to go and just trace the code and see the path it takes and see where the stack misalignment occurs. However, one thing that never occurs that I can tell is is where it finds a component. No. Yeah, I just have to see what's going on. It's very hard to know now. Gosh, it's coming along here. It's gotten farther and farther. So it should be able to do the 0 in the 1 solution case, and then it should get to the 3 solution case, and it's going to get an access violation just where we think it would. One idea, of course, is to just take a look at the stack and see what happened. Oh, RSP, not ESP. So, okay, I see stuff on the stack. Unfortunately, all the pointers I see on the stack. Well, we see yeah, everything on the stack looks. Okay, so one thing we can do is again this 9F is stack pointers on the stack, but again the question is these 1C9s. Yeah, these are the ones we're hoping for. But one's in this range, 220 something. 22D looks good. So this is the end of this is the last node. Okay, let's take a look. Let's get rid of the first two cases for the time being. Because we don't actually test the 0 variable formula. I said I should put it back in, just for the sake of being sure that I didn't screw something up in that. Because now we've narrowed it down to one area, and that's an important improvement. So we'll just start with that formula and set a breakpoint. Because at this point we can be confident that the next fix probably fixes the whole thing, unless we reintroduce bugs while fixing it. But I'm guessing it's a small problem here. So we want to take a look at what the stack is. And we see D98. And then I want to see what it is when it goes wrong, and we can start. So DA8. It's a bit weird because I don't see anything on the stack here. But I do see a stack misalignment, I think. No, I mean 90 could be conceivable. Okay, next check. How many does it do this all from the first call or not? Put a breakpoint here. Didn't happen on the first call. Second call? No. Third call? No. Fourth call? No. Fifth call? No. No. Sixth call. Yeah, I'm winding and weaving through this here. Wow, it's doing a lot of calls, and so we're at EO8 still. And so far, so good. Oh, I know what the problem is already, I think. Wow, it gets to the last call. So I can tell already what the problem is. Which means that my fix isn't going to work here. I have to think about this. This may be just a thinking problem for the time being. The problem is if we change this, uh, at least I think this is the problem. If we change this, we're going to have to do something about it. Because we have to not change it also. So it's like a swing dichotomy here. We want it to be C3 in one place, but we want it to be C2 in another place. It's like before calling it, we always want to make sure that it's right, but here we're changing it to C3. Actually, it's fine, because if it's C3, we don't even need to call it. It's pointless. So actually, there's another question of like, if we detect the return instruction already, why are we even calling it? I think that fixes it. Actually, that's pretty slick in a certain regard. So we, instead of do call, if it's equal, just don't call. Just don't do a thing. Ooh, now this could change some of the logic here. Don't call. We just changed the label. Compare it if it's a return. Don't call it. We don't even need to mess with the stack anymore, and we're done. Now, I don't know if this is going to mess up my code generator, but I hope it doesn't. But if I'm right, this actually solves it. That would be really nice. Whew. Seeing this actually work on the unlimited solution, well, not unlimited, but runs forever solution instance, that would be cool. Because then you know you really got it right. And then you can actually start profiling like little differences in the assembly code with large instances to really see what is fast with self-modifying code and what isn't in these little details. Of course, we have to rebuild the blueprint. We have to do everything again. But okay, so far so good. And again, it seems kind of risky, but we'll see what happens. It's annoying because actually this seems like we're getting an older bug coming back. Something that can, oops, something that can happen sometimes. I have no idea what's happening right now, though. Okay, we just take a look. We take a look at the simple case first. Obviously, this shouldn't be too hard to figure out. I didn't change much. Oh wait, it's supposed to be jump if equal. No wonder. The stack would be messed up if we don't do this correctly. Jump if equal. So we just need to change the call blueprint byte here from a 75 to a 74. See if we can get this to work. Oh, if we don't load racks, we can. Okay, I'm just blundering the code here. Move racks has to come first. Okay, which changes the offset as well. Yeah, it's annoying to keep doing this, but let's just do it. Because it's so exciting to see this actually get right after so many serious hours of work on it. Okay. Moving on. And action. So far, so good. Zero, zero, zero. 111, 33333. And it's a debug build, it's slow. Oops. Wow. That is so slow. STL in debug mode is it's atrociously slow. So we're not going to use STL. We're going to see that we did finish this. Wow. Okay, here it comes. Can we get 1,000 solutions per iteration out of it? And how will the performance be? So now it's doing the virtual machine version. So it took 0.9 seconds. I think that's actually elapsed time per 1,000 solutions. So it's not overall time. It's already been averaged. It's an average time. I should put that in the message. But what I'm really excited to see is the final result here. After all that monotonous complication, in fact, the comparison isn't that horrible, but yeah, I don't like it. But again, the fact that it works would be amazing. We'll see. Maybe it's going to crash here too. We don't know. But if it does work, that is truly fantastic. The fact that it came back on the 3 solution case, it gives it a high probability that it should work. If it doesn't, debugging it's going to be a nightmare because we need to find a better test case. We need to find general test cases that are, smaller than 100 nodes. 100 nodes, it's unwieldy. Wow, 6.5. Wow, look at how fast that is. Oh, wow. Oh, yes, that honestly, the self-modifying code is going to be competitive with the non-self-modifying code. Forget the virtual machine. Yes, it works. That's amazing. Oh, 1.89. Okay, we've got performance tuning to do, but not bad to generate an entire blueprint and to do all that work. Oh, yes, solved. All right, that was amazing. Okay, so I don't know. I said 1 hour before. It ended up taking me how many hours? I mean, this is just absurd, right? It's taken me I think more than 9 hours. No, 8 hours, 43 minutes. Just about the same length of time as the first half. So first half took 8.5, the second half took 8.5. This was intense programming. I enjoyed it though. And again, now I have a model. It's extensible. It's reusable. It's testable for like testing some ideas of can we save time by doing this, that, or the other. It shows how to do compatibility with the calling convention of lambda functions in C. We're able to actually directly call lambdas. The code is like pretty much ready for portability. There are some possible incompatibilities, but in general, it's simple, and the minimal amount of changes could be made to make it portable. In terms of 32-bit, there would be a bit more of a rewrite there, but not huge. I mean, of course, we'd still use virtualIC on Windows. In Linux, I'm sure it's the same call, 64, 32-bit. Mostly it would just be the pointer sizes, and of course the assembly language, completely different because different registers, and the RIP addressing really does change the uh, the exact semantics of how we do stuff. It's simpler though. As I point out, the 64-bit world, it's more difficult to do this kind of stuff, but we always have that move racks to an 8 bytes to always get away with anything there, and that's what I did. So yeah, thank you for watching this. That was really intense. Um, and wow, another 8.5 hour day and another task is solved, which accomplishes a huge amount, a chunk of research for me because, yeah, sure, there's going to be more technical issues, more hard stuff, but I mean, it doesn't get much harder than that. That was pretty much about as hard as anything you're going to end up doing probably with self-modifying code in assembly, without writing more tools to do the work. But just as a first get-go to say, I want to get it done, I want to do all the grinding, so that I have a model to work off of, it was worth it. If I'm going to do fancier graph algorithms, obviously I'm not going to do it this way. I'm going to find a better way to do it. But again, studying a problem, using the stack, beautiful. So thank you so much. And with that, we close this off. And let's check out what's going on in the world and what is going on is we're going to look at we're going to raid 1 lives left. Okay, there we go. And that's it. Thank you so much.